Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're done with the series on the formation of stars and protostars, so now we're going to learn how low-mass stars like the Sun evolve with time. Stars change during their long lifespans. Their histories reveal how they evolve as they furiously use up their finite but enormous amount of fuel from the moment they're born. Let's look at exactly how they do that. First, one thing to remember is that almost all stars in the sky are really quite boring. Well, boring if you're looking for massive explosions as viewed from Earth. Most of the stars, which can be derided as insanely boring, are so name-called because ultimately they weigh in at less than half the mass of the Sun. They do some really boring stuff that we'll chat about at the end. After the vigor of the Sun, it'll only take one slide to explain them. Thus, 85% of all the stars in the Milky Way can be explained with one slide. After we're done talking about the Sun and these other puny things, we'll go into really more dramatic things such as massive stars that populate the cosmos with heavy elements. But, to be fair, there's an awful lot of research done on these tiny stars because they're so numerous that they might even be havens for exoplanets that might shelter life outside the solar system. So let's begin our journey into stellar evolution with how a star like the Sun changes with time. And so once again, let's start over with the life cycles of stars. This excellent infographic comes from the Chandra Group at Harvard. We see that the mass goes from the low-mass stars at the bottom of the graph to the high-mass stars along the top. We see how stars evolve as time progresses from left to right. Just like in the previous lectures on starbirth, we see there's different flavors of protostars. The more massive the protostar, the shorter the time it takes for them to collapse down into a star, and they end up doing something very different. But we're getting ahead of ourselves. We're going to be talking about the bottom three tiers. At the bottom are the brown dwarfs, which don't really seem to do much during their lives. That's not entirely true. So what happens to brown dwarfs? If the protostar is less than 8% of the mass of the Sun, or 0.08 solar masses, this brown dwarf will never initiate fusion in its core. It simply contracts like a protostar under gravitational pressure, releasing heat via the Kelvin-Helmholtz mechanism. We talked at length about this in my lecture on the Sun and in the Starbirth series. Amazingly, a brown dwarf will do that a very long time. It's the closest thing to forever for a brown dwarf to do its mellow thing. Brown dwarfs can also be called hot Jupiters, and there are a large number of massive exoplanets that have been found around other stars that are basically in the in-between zone of a planet and a star. These non-stellar objects make up a huge number of the objects in the Milky Way. Next, second level, we have the red dwarfs, which will eventually become white dwarfs. These live between 8% and 25% of the mass of the Sun. They do fusion in their core, with the least massive doing so just barely. But these just barely stars make up between 75 and 80% of all the stars in the Milky Way. We don't see them in the sky without telescopes because they're far too dim. Next is the primary subject of this lecture. Looking at the third tier, the protostar becomes a sun-like star and then becomes a red giant, and its closing epochs forms a planetary nebula, and finally a white dwarf. We'll talk about some of the other stuff up above next time. We see that stars have cycles of birth, youth, middle age, decline, and death. So the source of life of nearly all stars is hydrogen fusion in their cores. Every star that you see in the night sky, and most you don't, is fusing hydrogen into helium in its core. However, many of the visibly brighter stars, such as Betelgeuse and Bellatrix, shine by fusing helium in their cores. But the question that concerns us today is what happens when a star's hydrogen is used up and converted into helium? Then what happens to the star after all this helium is created? Well, for stars like the Sun, the core is too cool to ignite helium fusion. And by hot, we mean, of course, that the helium nuclei in the core are not moving fast enough to have a decent chance of overcoming the Coulomb barrier and therefore quantum tunneling into close enough proximity to fuse. This all means that an inert helium core is slowly building up in the center of the Sun. The main sequence lifespan, which says the same thing as the length of time a star is burning hydrogen, is determined by how much hydrogen is available to fuse in the core. Throughout this chat, I'll loosely conflate the word burning with fusing. The hydrogen fusion or fusion bursting lifetime of a main sequence star like the Sun will last about 10 billion years. Such stars are about one solar mass. The little M circle dot means that is the unit of a solar mass. But if the star is just barely clocking in at a tenth of the mass of the Sun, then such a star can live up to about 10 trillion or 10 to the 13th years. This is an incredibly long time. The universe itself is only about 13.7 billion years old, which means that literally zero of all the stars in the 0.08 to about half solar mass have run out of hydrogen in their cores. Further, these are all red dwarfs. They are the dimmest and most common stars of all. So the evolutionary cycle of the Sun follows the graphic across the top. For about 10 or 11 billion years, the Sun is a main sequence star. Then for about 1.25 billion years, it's a red giant, where it grows to be roughly the size of Earth's or Mars's orbit. Then it becomes a horizontal branch red giant star for about 100 million years, in which it's stably burning helium. As it runs out of helium, it rises in luminosity to become an asymptotic giant branch star for about 20 million years. At this point, the helium has run out and it sputters like a car with an empty tank and pulses itself apart over about 500,000 years, with the outer envelope all becoming a planetary nebula, which dissipates away after about 10,000 years. At the end of this lifespan, it will be a white dwarf. This white dwarf will only have about half the Sun's original mass. All the rest will go out into space and enrich the interstellar medium with carbon and nitrogen and oxygen and, of course, hydrogen and helium. Right now, the Sun is about 4.5 billion years into its main sequence life of approximately 11 billion years. Amazingly, we know this because of the ages of carbonaceous meteorites with chondrules and calcium aluminum inclusions that date them at 4.567 billion years old. CAIs are 30 million years older than the Earth and about 140 million years older than the oldest rocks known on Earth. The Earth, Sun, and all the planets form from the same nebula, and such meteorites solidify directly from that nebula and live far enough from the Sun to never melt. Anyway, let's look at the age of the Sun. In the center of the Sun right now, the core is burning hydrogen. This is the fusion of hydrogen into helium via the proton-proton chain process. This is possible because it's roughly 15 million Kelvin in the core. If it was a little hotter, perhaps 18 million Kelvin, then the Sun would be burning hydrogen through the CNO cycle. As it stands, the Sun only gets about 2% of its energy from the CNO cycle. I discussed this at length in my video about what's going on inside the Sun's core. Stars like the Sun will do this for about 11 billion years. The current structure of the Sun at 4.567 billion years old, it has an inert helium core down in the center. This helium is the hot ember of the hydrogen fusion that's already occurred. As hydrogen burns to helium, it sinks to the center and doesn't participate in anything at all. In fact, it's getting more and more compressed as time goes on, growing in its degeneracy. The core is completely composed of helium. Surrounding this inert core is a hydrogen-burning zone that's still part of the core. This energy transport mechanism of the core region is purely radiative, which I've indicated with the reddish zone. The blue fusion core is also radiative support. That zone is where the fusion occurs. This merges pretty smoothly with the convective zone above it, and it's important to note that the Sun's core does not mix with the convective zone. The convection does not go deep enough. What's down in the core stays in the core. Of course, at the top of the convective zone, that's where we see granules and supergranules and the photosphere, as well as all the active regions on the surface, what we call the surface of the Sun. When the star starts to run out of hydrogen, that's when it leaves the main sequence. Before then, during the main sequence life, two things are always in balance. One, there's a gravitational pull that's pulling the star together, which is balanced by the outward pressure due to the heat coming from the center. Remembering our 9th grade chemistry class, if you have an ideal gas that heats up a little bit, then the gas will expand. Once this gas has expanded to accept the additional heat, if it can radiate away this heat, it'll contract again. For a star, the source of this heat is fusion, and a star can expand since it is gaseous and not a solid or liquid. If a star expands due to additional heat from the core, then that relieves the pressure, allowing the core to cool. This in turn means less heat is generated, and this means gravity starts to win and contracts the gas as it cools. Gravity wins until fusion kicks back in with enough energy to expand the gas above the core again. In this way, there's a continual battle between the inward pressure due to a star's self-gravitation and the outward pressure due to the heat provided by the fusion in the core. After a star is settled into the main sequence after its protostellar phase, this balance is very good. So good, we don't see the Sun pulsing radially. The energy output from the core exactly matches the energy lost to space. We call this balance of energy supplied to energy lost thermodynamic equilibrium. Also, we call the lack of pulsation due to the balancing of outward gas pressure against the self-gravity of the star hydrostatic equilibrium. On the main sequence, these two equilibria hold true. But when the core starts to run out of fuel, then both balances begin to break down and the star leaves the main sequence. Here's a more detailed view of the conditions and timings of the evolution of a one solar mass star, such as the Sun. These numbers come from computer models of the various well-known physics relations pertaining to stars. We can look at the first column, and we see that the main sequence lifetime is easily well over 100 times longer than the post-main sequence phases, particularly when the red giant and subgiant stages are taken together. Since we're looking at the transition between the main sequence and the final state, meaning a white dwarf that eventually cools off to a black dwarf, we see that this shorter epoch will fill the Sun with change. Even though the surface temperature doesn't vary a huge amount during the change, that's not the whole story. We see that the core density steadily rises as the fusion products are compressed in the core. The size of the Sun will also radically change. When it first becomes a red giant, it'll swell to the size of Venus' orbit, and during the asymptotic giant branch phase, it will exceed the Earth's orbit. The glowing planetary nebula itself will expand to nearly a light year, with the central part of the nebula going to Jupiter's orbit. It will end its life as a core about the size of the Earth. As we see from the Stefan-Boltzmann law for stars below, small changes in the surface temperature will lead to big changes in the luminosity. But a real change for the Sun's future luminosity will be the radius change, when, for that short period at the AGB peak, the Sun will be one of the brightest stars within a couple thousand light years, illuminating distant worlds the way red giants Betelgeuse, Antares, and Arcturus do for our night sky. So how do we determine how the Sun evolves? Researchers using computer code create models using the equations of stellar structure that I showed you in my previous lectures on the interior of the Sun. Plug all this into large computers and let it cook for a few hours or days. These large simulations take as inputs the surface parameters of the Sun, such as known mass, observed luminosity, surface composition, and radius, and munge them up to show how things will change as a function of mass fraction inside the Sun. Combining this with the methods of energy transport, such as radiative and convective transport, shows how the Sun retains and loses its energy to space. These simulations then check what happens as fuel is used up in the core. The model is usually run for time slices on the mass fractions. First, you have to solve the entire Sun for given conditions from surface to core and core to surface, then advance each slice in time, specifically the core, to see how the interior conditions change with time. The models take so long to run because one needs to vary the steps in time and radial mass fraction. This dynamic grid modeling is quite computationally intensive. Luckily, today, unlike back when I was in grad school, you can spin up a bunch of nodes on AWS and run it together if you're on a skimpy university budget. Then, this all takes a huge wad of numbers which are the map of the inside of the star, and it shows you how it changes with time. Below are some papers you can look up if you want to go take a peek at some of the published models of the evolution of the Sun. Let's watch the Sun evolve as determined by these huge simulations. Included in these simulations are observational matchups, meaning that there is something in the sky today that has been observed with the characteristics of the Sun that we'll be discussing. I'll be describing one such model to a great extent. 5 billion years ago, the Sun formed from a dense molecular cloud, such as Barnard 68, or other such dark clouds that we've seen, the Bok globules. It took about 50 million years to form from this stellar cocoon, finally reaching the main sequence at about 4.5 billion years ago. This is the ZAMS, or zero-age main sequence, when the Sun first alit onto the main sequence and started burning hydrogen in its core. At this time, it was very different than we see today. It was a little fainter at about 70% of a solar luminosity. It was a little smaller at roughly 9/10 of a solar radius, and a little cooler at 5580 Kelvin rather than 5800 Kelvin. At this point, the zero-age main sequence, when hydrogen initiation occurred, the Sun came to thermal and hydrostatic equilibrium. What we'll show is a sketch of the Hertzsprung-Russell diagram, and on this we'll plot a track that shows how the Sun's temperature and luminosity changes with time. The Sun is currently a middle-aged low-mass star on the main sequence. Its age is well known by meteorites to be 4.567 billion years, or 4.5 times 10 to the ninth years. Its mass today is our standard unit of mass, the solar mass, which is about 1.99 times 10 to the 30th kilograms. We also use the solar radius as a standard unit of measurement. Its radius is about 700,000 kilometers, or 100 Earth radii. That means end-to-end 100 Earths could fit across the sun. Makes you think about the sizes of sunspots, like the ones you're watching in these images from NASA's Solar Dynamics Observatory. The luminosity of the sun is about 4 times 10 to the 26th watts, which is much more than the human race could generate in 1 trillion years. This solar luminosity is also a standard unit we'll see over and over again in this lecture series. The surface temperature is 5,800 Kelvin. Half of its core has been fused into helium, so there's an enormously large inert helium core in the center of the sun today. The sun at this time is in a state of hydrostatic and thermal equilibrium. The energy that's being lost from the photosphere as light is balanced by energy being produced in the core, and the sun's not getting larger or smaller in size. This is the way of the sun for about 10 billion years. During the sun's main sequence life, the hydrogen-burning part of the core fuses hydrogen into helium using the proton-proton chain at a temperature of 15 million Kelvin. Surrounding the core is the convective zone, with a buffer of a shallow radiative zone separating them. While the appearance of the sun by this diagram makes it seem like the mass might be smoothly distributed, half of the mass of the sun is in the core region. That inert helium core will become important very soon. Even while on the main sequence, the composition of the star's core is changing. Eventually, as hydrogen in the core is consumed, the star begins to leave the main sequence. Its evolution from then on depends very much on the mass of the star. The diagrams show the percentage of hydrogen in orange and helium in blue. We see the percent going from bottom to top, 0 to 100, and the radius increasing to the right, with the core on the left and the photosphere on the right. The top panel shows the composition at the ZAMS, the zero-age main sequence. The sun's original composition was inherited from the interstellar medium from which it formed. From the studies of the local interstellar medium, originally it would have had about 71% hydrogen, about 27% helium by mass. The remaining 2% was other elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. But by number, it started off as about 92% hydrogen, about 8% helium, with all the other elements contributing less than 0.1% of the remaining nuclei. The middle panel shows the distribution today. The composition of the photosphere at the right side of the diagram by mass is 74.9% and helium is 23.8%, which means that some of the helium has settled down into the core due to gravity since the sun's birth. We can see that the blue slab of helium in the core has increased from its original 24% to now about 60% of the mass of the core due to fusion. The core is the only region of the sun that produces an appreciable amount of thermal energy through fusion. 99% of the sun's power is generated in that inner 24% of its radius, and almost no fusion occurs beyond 30% of the radius. The convection starts at about 45% of the radius, so the products of the core do not show up in the photosphere during the main sequence life. The bottom panel shows the state of the sun's composition after 10 billion years. The core will have expanded and the hydrogen will be gone from the core. The blue fraction of helium that has moved away from the central 30% shows something's happened to the location where fusion occurs. It's moved closer to the surface. At this point, the sun will evolve quickly. Now let's look at the future events according to these models. When a sun-like star reaches an age of about 10.9 billion years, and for the sun, that'll be about 6.25 billion years from today, the star's core will have run out of hydrogen. Then, most of the core's volume will have been replaced by an inert helium ash. As a result of the massive weight bearing down on it, this inert helium core will contract and heat up. Even still, it does not ignite helium fusion. To keep the star from collapsing then, the hydrogen burning moves out into a shell around the core. This shell burning has observable results. At the surface of the star, the temperature will drop to about 5,500 Kelvin, and the size will grow to about 1.6 times the radius of the sun, and the luminosity will increase to about 2.25 times the luminosity of the sun. These three parameters are interrelated via the Stefan-Boltzmann law applied to stars. Physically, its luminosity and radius grow because the fusion source is now closer to the surface. The luminosity increase means that there's greater energy production happening in the core due to these extreme internal changes. As we now follow the track of the Sun into the future, we will see how its appearance will change. The time steps will not be the same between each location on the track as we go forward. It'll just be the path it takes. This path denotes all the observable changes that will happen due to the events and changes happening in the core. Every star will make such changes, and we'll see in future lectures how different stars make different tracks. In our current example, in 6 1/3 billion years, the Sun will leave the main sequence, becoming a subgiant star. So what is this shell burning, and why does it increase the luminosity? All right, so as the Sun runs out of hydrogen, there's less fuel in the volume of the star's core where fusion can occur. Also, the volume of fusion-capable core that's not occupied by inert helium is getting smaller. It's this combination that demands that the average kinetic energy of a given hydrogen nucleus, whether it's a proton or deuterium or even a light helium nucleus, all must be higher. This is because the same top pressure, due to all the same overlying material, the components of the proton-proton chain must move faster and faster just to find other components in order to complete the fusion process. Well, it's not like the nuclei are seeking each other at some speed dating session for lonely singles. There's no intent to them. It's just that in order to maintain hydrostatic and thermal equilibrium in the star, the components of fusion don't encounter each other often enough unless they're going faster. So we can equate the average kinetic energy, 1/2 mv squared, resulting from the faster speeds of the nuclei to the average thermal kinetic energy, 3/2 kBT. We see that the temperature must increase. With an increased temperature comes an overall increase in energy output by the Stefan-Boltzmann law for a black body. Since this will necessarily heat the gas above the hydrogen-burning shell, it will expand, lifting some pressure off the core. The star's radius will grow until the pressure decreases enough to balance the energy output of the core. But a larger star with a higher luminosity all means that the star is getting brighter. The reaction of a star to running out of fuel is therefore to burn brighter and hotter. Now, while the core temperature is increasing, the surface temperature decreases because the star is getting physically larger, better allowing heat to escape. On the HR diagram, it moves up, more luminous, and to the right, cooler. All the while this is happening, the central core is becoming quite important to the star. The innermost 3% of the star's mass fraction must be all at the same temperature. This isothermal core supports all the weight above it. To do so, the density must greatly increase down to the very center. As the hydrogen-burning shell dumps more ash on top of it from above, the mass fraction of the isothermal innermost inert core grows relative to the entire star. The innermost 3% total core depletion of hydrogen with shell burning around it will be the state of the Sun when it's 9.8 billion years old. The weight of all the star will keep pushing down on this isothermal pure helium core for another 1.5 billion years. For these next 1.5 billion years, the Sun is now what's called a subgiant star. It expands radially in size, keeping a near constant luminosity of about 2.2 solar luminosities and inches towards the base of the red giant branch. To do so, it swells in size from 1.6 to 2.25 solar radii, which cools the surface layers from 5500 Kelvin down to 4900 Kelvin. This huge growth of the outer layers means that it's not held on as hard by gravity. Therefore, this lateral move across the HR diagram is accompanied by the start of a slow mass loss in the form of a stellar wind. As time progresses and the star increases in size, this wind will pick up steadily. This marks its approach to the base of the red giant branch. It's interesting that the luminosity stays the same given what I just described, but here the mass loss is now a balancing factor. Since the luminosity is not changing, then conditions in the core must be changing in some new way. More helium ash is building up in the isothermal core, but the core is now strongly compressing, and this compression is still mostly according to the ideal gas law, but that will change soon. Importantly, it is this foundation at the core that supports the entire star by increasing the pressure down to the very center without producing any new energy. The volume where the conditions are ripe for hydrogen fusion above the core remain roughly the same. As more nucleons fall into the region from above, the core contracts below as the newly created helium falls. The larger radius arises because the mass loss takes away the inward pressure due to gravity. The stellar wind mass loss is driven by that huge heat output that is coming from this ever-increasing temperature of this shallow fusion layer. Looking again at our equation, a larger radius but with the same luminosity means lower surface temperatures. The end of the road for this arrangement happens when the isothermal core reaches 8% of the mass of the entire Sun. That's where our limit of the additional 1.5 billion years comes from. Now the Sun is 11.4 billion years old and the core can no longer support the weight above it. It now collapses on the Kelvin-Helmholtz timescale. At this point, there is no nuclear fuel, so the only way to provide heat is to collapse and convert that energy into heat then light. The total gravitational energy of the Sun's inert core divided by the luminosity needed to add to the shell burning to keep the Sun from runaway freefall gives us a time. This time is how long the Sun will be able to support itself in this way, which is only about 900 million years. This collapse of the core marks the very beginning of the subgiant phase of the Sun's life. This subgiant phase obviously must end. This constant luminosity, increasing radius, decreasing temperature phase ends about 250 million years later. And it does so when it starts to become a red giant. While the core collapses and compresses the outer layer, the greatly expanded outer envelope decreases in temperature. This allows the increasing creation of what we call a hydrogen minus ion in the envelope, or an H minus ion. This ion is basically a hydrogen atom with a loosely attached second electron. This wacky-sounding ion radically increases the opacity inside the star. And this increase in opacity creates a very deep convection zone inside the star that goes from the surface photosphere all the way down to where the Sun or any star of its mass has created a lot of fusion products from the CNO cycle. This convection is so efficient at transferring energy throughout the star that the outer envelope increases in size even more. Deep in the core, the helium core is still collapsing, getting denser, and releasing its gravitational potential energy as heat and light in a desperate attempt to keep the star from collapsing. And as it does so, it's starting to use a new trick, though, electron degeneracy. In order to know what electron degeneracy is, we first have to look at normal gases. Well, what's a normal gas? Of course, it obeys the ideal gas law, shown here with a simple relationship between the pressure, density, and temperature. Now, the Sun and all stars are fully ionized gases, but the ideal gas law is a good approximation for what goes on inside them. This diagram shows the effect of what's called the Pauli exclusion principle. It states that no two particles in a system, fermions here, can have the same 6 quantum numbers of momentum and position. And by fermions, suffice it for now that this includes electrons, protons, and neutrons. Each of these 6 quantum numbers corresponds to a physical location denoted by the canonical x, y, and z directions, and to the momenta in each of these directions. Each momentum is determined by the particle's de Broglie wavelength. In addition to these 6 quantum numbers, fermions get yet another quantum number, spin, which has 2 states, either 1/2 up or 1/2 down. Why exactly it's 1/2 and why it's up and why it's down, that's a different conversation. Suffice it to say that this diagram is a radical simplification of all this, showing only one spatial freedom and one energy state corresponding to the momentum in one direction. We're just looking at the position and momentum in one physical direction, say x, or perhaps left-right. These are the available quantum states in our super simple model. And we're only going to stare at the quantum states for the electrons. The protons and neutrons have their own boxes. In each box, or quantum state, the arrow up or down indicates that electron's spin. Now, if we really want to do this right, we'd need a 6-dimensional cube to get all of the quantum states in the entire phase space. But as you can see, a normal gas has a pretty good distribution of high and low energy electrons with a mix of ups and downs. There's lots of freedoms for electrons to gain and lose energy, and lots of places to go. Basically, in a normal gas, all the available quantum states far exceed the total number of electrons in the available 6-dimensional phase space. An electron can easily lose a lot of energy, come to a near stop, but it'll likely get bonked by another electron and jump up high again soon. There's just a lot more open slots than there are electrons. So what happens when you take the energy away from a gas? It gets colder and more compressed. Here we see a very, very, very cold fermion gas. As the temperature drops, the lowest energy states start to fill up. Because fermions in the same system cannot be in the same quantum state, that is, some combination of location, momentum, and spin, they begin to stack up. Some of these electrons retain a lot of energy, even though they've lost all they can. This is because there are no available lower energy states. At temperature equals 0, none of the higher energy states are filled, and all of the lowest ones are completely filled. And this is what we mean by a degenerate gas, and it most certainly does not behave at all like an ideal gas. And it's not just as if it's extremely cold. Extraordinary pressure can force the electrons into this degenerate state, but the result is the same. The inherent heat energy that was in the random motions of the previous ideal electron gas has been sucked out of the system. This provides an extremely strong lattice structure which can now provide the support for the star's weight above it. Remember, this is just the electrons. The protons, neutrons, and other fermionic nuclei could, and in the case of stars are, still in a near-ideal gas law state. The heat energy of the electrons was simply sapped into the layers above the core to keep the rest of the star aloft. In sum, a degenerate gas can occur at extremely high densities, and when it does, this new gas law takes over. This is the equation for a degenerate gas. I want you to note a few things. First, the only two macroscopic variables are the pressure on the left and the mass density on the right to the 5/3 power. All the rest are numbers and constants. M sub E is the mass of an electron. M sub H is the mass of a hydrogen atom. Z over A represents the ratio of the atomic number Z to the atomic mass number A of the nuclei in the gas. Importantly, the pressure is now independent of temperature, and increased compression doesn't lead to heating. This means that the objects could, in principle, be very cold but still have enough pressure to maintain a state of hydrostatic equilibrium. The inequality across the bottom shows the crossover point between a normal gas and significant degeneracy. Here, T is the star's core temperature and ρ is the core's density. If this ratio is less than that number, then it's mostly degenerate. Currently in the sun's core is not degenerate since that ratio is about 5,500, but something like the PUP, the white dwarf orbiting Sirius, is. Its value is extremely below the boundary, so it's fully degenerate. As for solar mass stars, when they begin to climb up the RGB, or the red giant branch, their cores contract and cool off and get increasingly dense. Eventually, these cores become fully degenerate gases. In fact, a core such as this actually cools down in the center of the star, getting a temperature inversion from the outer core to the very center, principally due to neutrino losses from deep in the core. Getting back to the exterior view of our star. As the star climbs the red giant branch, the convection zone continues to deepen. As we saw a bit ago, the base of this convection eventually reaches down into the regions where the chemical composition has been modified by nuclear processes. In particular, lithium burns via collisions with protons at relatively cool temperatures, and because of its rather large nuclear cross-section for reactions, this temperature necessary for the reaction is just below the temperature for hydrogen fusion via the proton-proton chain. Therefore, this has been happening as a minor energy source since its time as a protostar, and during this lithium burning, its most abundant isotope, lithium-7, collides with the proton and produces beryllium-8, which then quickly decays to become 2 helium nuclei. In so doing, lithium has become nearly depleted over most of the star's interior. Next, this shell-burning phase of the subgiant and red giant branch phases mean that the mass fraction of helium-3, light helium, over the middle third of the star has also increased a lot. We didn't talk much about the CNO cycle for the Sun, but it's occurring in small quantities, which means that the core would be enhanced with carbon, nitrogen, and oxygen. All this deep fusion transformation stayed in the core region for all of the star's life, but when the surface convection zone reaches deep into this chemically modified region, the processed material becomes mixed with the material above it, and we can observe the changes in the composition of photospheres of red giant stars, compared to their same mass main sequence counterparts. Astronomers have observed that the amount of surface lithium is lower and the helium is more abundant. Additionally, carbon-12 is dragged down and depleted at the surface, and nitrogen-14 is raised up and is more abundant. Astronomers typically look at these as ratios, such as X12 for carbon-12 and X14 for nitrogen-14, which correspond to the relative depths of absorption features for the carbon-12 and nitrogen-14 observed in stellar atmospheres. It is observable ratios like these that demonstrate the transport of materials from the deep interior up to the surface. This change is called the first dredge-up phase. The first here doesn't imply that all stars do the first and then the second and so on. The first here is another astronomerism. It means the dredge-up of these elements to the surface in this process. More massive stars might skip this dredge-up entirely, doing other dredge-ups, which we'll cover later. What's amazing is that nature provides us with this means of directly observing the products of nuclear reactions deep within stellar interiors, and it is these observable changes in the surface composition that provide important tests of the predictions of stellar evolution theory. After 600 million years of climbing the red giant branch, it reaches the tip. For the Sun's future, the photosphere has made a radical transformation. The outer envelope has expanded to over 160 times that of the current radius. That's about 3/4 of an astronomical unit and would engulf the orbit of Venus. Both Mercury and Venus would be inside the Sun, spelling their doom and destruction. The Earth won't be doing any better, and the mass loss from the Sun will be changing its orbit, steadily dragging it in. The surface of the Earth will be completely molten, all the water on Earth will have been gone already for billions of years, and sentient life will have needed to have moved on long ago. The Sun will have grown in luminosity to well over 2,300 times its current luminosity, which would make the gases of Jupiter and Saturn boil away, leaving their strange cores exposed. The corresponding drop in surface temperature to about 3,100 Kelvin means that the Sun will no longer be a golden G25 star, but will now be a garnet-colored M03, matching the colors of Antares and Betelgeuse in the sky. Down in the core, at the tip of the red giant branch, the central temperature and density have become about 10 to the 8th Kelvin and about 7.7 times 10 to the 6th kilograms per cubic meter. This is now high enough that quantum mechanical tunneling through the Coulomb barrier between helium-4 nuclei becomes effective, allowing the triple alpha process to begin. This is a new fusion process for the star. It is the fusion of 3 helium nuclei into carbon. All this helium has accumulated in the core as a result of the proton-proton chain reaction, and the carbon-nitrogen-oxygen, or CNO cycle, is now available for use. The first fusion reaction of 2 helium-4 nuclei produces beryllium-8. Now, beryllium-8 is very unstable and will decay back to smaller nuclei with a half-life of about 8 times 10 to the minus 17th seconds. But if, before it does so, it encounters another alpha particle, it may fuse with it to produce carbon-12. This first reaction is endothermic, meaning it takes energy to do. So in addition to being a huge electrostatic barrier to overcome, there's a need for additional kinetic energy from the nuclei to create that beryllium nucleus. That kinetic energy comes from the high temperature of the nuclei as a gas. This temperature and subsequent thermal motion must be so high as to provide about 92 kiloelectron volts, which is the equivalent of a high-energy X-ray photon. This gas has to be hot. Luckily, the second step, which has to happen fast before the beryllium decays, is exothermic, releasing a high-energy gamma ray. It is this release of energy that is the new fusion source. Because of these conditions for this process, a high Coulomb barrier for the first step, a need for additional energy to create the beryllium nucleus other than just the 2 input parts, and a fast decay rate demanding a fast find of a fusion partner in this hellish do-si-do, all means that this whole process is extremely temperature dependent. The triple alpha fusion reaction rate goes like temperature to the 40th power. That is, if the temperature rises by 10% when it's 100 million Kelvin, then the fusion rate goes up 45 times. If the temperature happens to double to, say, 200 million Kelvin, then the fusion rate goes up 1 trillion times. It also means that if the temperature dips lower than 100 million Kelvin, the process shuts off completely. Triple alpha is a cauldron of chaotic fusion. At this point, an interesting difference arises between the evolution of stars with masses greater than about 1 solar masses and those with masses less than 1.8 solar masses. For stars of the lower mass bracket, as the helium core continues to collapse during evolution up to the tip of the red giant branch, the core becomes increasingly electron degenerate. Furthermore, significant neutrino losses from the star's core before reaching the tip of the red giant branch result in a temperature inversion near the center, cooling it relative to the layers above where the hydrogen shell burning is happening. When the temperature and density become high enough to initiate the triple alpha process, again, this is about 10 to the 8th Kelvin and 10 to the 7th kilograms per cubic meter, respectively, the energy release in such stars is explosive. The ignition of helium burning occurs initially in a shell around the center of the star, but the entire core quickly ignites, blowing away the core's temperature inversion. The luminosity generated by the helium-burning core reaches 10 to the 11th solar luminosities, comparable to that of an entire galaxy. While extreme, this tremendous energy release lasts only for a few seconds, and most of the energy never reaches the surface. It's absorbed by the envelope above, perhaps causing a short burst of mass loss from the surface of the star, but in general, this event is hidden from view and has never been seen observationally. This is called the helium flash and occurs only in low-mass stars. It occurs because of the combination of the basically non-existent temperature dependence of electron degeneracy pressure and the extreme temperature dependence of the triple alpha process. The flash's energy must go first into lifting the degeneracy, turning the electrons back into an ideal gas law state. This phase transition takes a lot of energy. Only then can the energy go into thermal and kinetic energy. Once it does, the core then expands, which decreases the density. A lower density then lowers the temperature, which in turn then slows this crazy reaction rate. Now that these stars burn helium, the extra energy stabilizes the core against collapse. In addition, there's still hydrogen burning in a thin shell outside the helium-burning core. This hydrogen-burning shell remains the dominant source of the star's luminosity. The core helium fusion allows the core to expand, and the core's expansion pushes the hydrogen-burning shell above it outward, cooling it and therefore causing the shell's energy output rate to decrease slightly. This energy output results in an abrupt decrease of the star's luminosity as seen from the outside. The lower luminosity allows the envelope to contract and the effective temperature to increase. This process means that the star will descend quickly into a new region of the HR diagram, the horizontal branch. This whole thing happens fast, lasting only about 1 million years. At this point, I want to point out that you can find much of this material in Carroll and Ostley's excellent undergraduate textbook, Introduction to Modern Astrophysics. This book is the standard textbook for all astronomy majors. At this new phase, there is a helium-burning core with a hydrogen-burning shell for both low and intermediate mass stars. Here, the increasing compression of the hydrogen-burning shell eventually causes the shell's energy output and the star's overall energy output to begin to rise again. In this period on the horizontal branch, the star is in a newer, shorter phase of hydrostatic and thermal equilibrium. The radius of the star is about 10 solar radii, and the temperature is much less than the current solar temperature of about 4,700 Kelvin, and the luminosity is about 40 times that of the luminosity of the Sun. With this associated increase in surface temperature that we found from before, the envelope's convection rises towards the surface. Now, a new convective core develops. This convection arises again because of the steep temperature sensitivity of the triple alpha process. These things combine to push the envelope to be hotter at the surface, causing a blueward horizontal evolution along the horizontal branch. At this time, it's the helium-burning analog of the hydrogen-burning main sequence, but with a much shorter timescale. For Sun-like stars, this blueward advancement only lasts about 100 million years, and while it goes on, the star is quickly building up a carbon-oxygen core, which is still too cool to ignite carbon fusion. Now I want to backtrack just a little bit. Let's take a closer look at something that's already happened back in the main sequence lifetimes of stars that are just a bit more massive than the Sun. It's important to note that many Sun-like stars use the CNO cycle instead of the proton-proton chain for nuclear reactions. Now, the Sun only gets about 2% of its energy from the CNO cycle, but in slightly larger stars, about 1.1 solar masses or more, CNO accounts for 50% and then dominates the energy production at all higher masses. Just like the proton-proton chain, the net result is a conversion of 4 protons into 1 helium nucleus with a release of energy in the form of gamma-ray photons, neutrinos, and positrons. This process does not consume carbon-12. It goes in at the top and comes out at the end. We say it acts as a catalyst. And because carbon and nitrogen have 6 and 7 protons respectively, in order to overcome the repulsion of all these positive charges, the protons must be moving very fast. Because the temperature in a fully ionized gas is directly related to the average speed of the particles of the gas, this is why the CNO cycle occurs at higher temperatures than the proton-proton chain. The limiting reaction is the 4th step, where nitrogen-14 captures a proton. This is because nitrogen-14 has a very small cross-section with respect to all the other things in this chain. This means there can be a measurable buildup of nitrogen-14 during the course of this reaction chain. The next phase of the evolution is very similar to the evolution following the exhaustion of the hydrogen-burning core. It starts to turn redward again on the HR diagram until it starts to bend upward along a path referred to as the asymptotic giant branch, or AGB. The AGB is so named because the evolutionary track approaches the line of the red giant branch asymptotically from the left. The AGB can be thought of as the helium-burning shell analog to the hydrogen-burning shell red giant branch. At this point in the evolution, the core temperature of, say, a 5 solar mass star is approximately 2 times 10 to the 8th Kelvin, and its density is on the order of 10 to the 9th kilograms per cubic meter. This means during the early asymptotic giant branch, a star has 2 shell sources. Although the 2 shell sources are depicted, it is the helium-burning shell that dominates the energy output throughout the early asymptotic giant branch. The hydrogen-burning shell has become nearly inactive at this point. Note that the diagram is really not to scale, and to visualize the structure from the hydrogen-burning shell inward, I've had to cartoonify it and greatly enlarge it relative to the surface of the star. The expanding envelope initially absorbs much of this energy produced by the helium-burning shell. As the effective temperature continues to decrease, the convective envelope deepens again. This time it extends down into the chemical discontinuity between the hydrogen-rich outer layer and the helium-rich region above the helium-burning shell. This mixing results in a second dredge-up phase, which increases the helium and nitrogen content of the envelope. This nitrogen comes about from the incomplete CNO cycle I described before. In fact, when running stellar evolution simulations to equilibrium, there's always an excess of nitrogen-14 because of its small interaction cross-section with proton collisions. The enhanced nitrogen-14 has been observed in red giant stars, which confirms the existence of the CNO cycle and again tests these stellar evolution theories. Our Sun-like star is now rapidly climbing the asymptotic giant branch, or the AGB. During this brief 20 million years, its carbon-oxygen core will steadily contract and heat up. Nuclear fusion is only occurring in a helium-burning shell, and above it lies a mostly helium non-burning shell with a thin, nearly dormant hydrogen-burning shell above that. Externally, the Sun-like star swells, becoming cooler and brighter. It will be brighter than its previous ascent up the red giant branch, and it will occur much faster than 20 million years compared to 600 million years. If this were the Sun, then its outer layers would expand to about 85% of an astronomical unit, once again nearly to Earth's orbit. The Earth would no longer be there to greet its increase, having been aerodynamically dragged into its doom during the red giant phase. Now, it's likely Mars's turn to fall inward. Generally, for such stars, the surface temperature drops to about 3200 Kelvin, but the luminosity significantly increases due to the core's incredible heat generated by the helium shell burning. This enhanced luminosity leads to a shorter lifespan in this evolutionary phase because faster burning equals a shorter lifespan. As it reaches the upper portion of the asymptotic giant branch, The quiet hydrogen-burning shell reignites and dominates the star's luminosity source. This time, however, the helium-burning shell is being forced to occupy an ever-narrowing layer of the star's core. It also begins to detonate on and off semi-periodically. These repeating helium shell flashes occur when the hydrogen-burning shell dumps helium ash onto the helium layer below, increasing the mass and forcing it to become slightly degenerate. At some point in this dumping, the temperature at the base of the helium shell increases enough to cause a helium shell flash. This is close to the same process as the helium core flashes of low-mass stars, but without their huge energy output. Each flash drives the hydrogen-burning shell outward, cooling it and temporarily shutting it down. Once the helium shell burning calms down, the hydrogen-burning shell turns back on, and the cycle starts all over again. The time between each pulse depends on the mass of the star. Higher mass stars, around 5 or so solar masses, can do pulses every few thousand years. But low mass stars, down to about 60% of a solar mass, can take hundreds of thousands of years between pulses. Importantly, each pulse is stronger than the previous. The graph that you're looking at comes from a simulation for a star with about 60% of the mass of the Sun, and it comes from a 1982 Astrophysical Journal article written by Iko Ibn, a pioneer for such stellar interior modeling. It details the luminosity as a function of time. This sequence for a low-mass star lasts about 2.5 million years. You can clearly see the effect of the flash radically increasing the luminosity, followed by a sharp drop in luminosity, which are the spikes in the graph. Near the tip of the AGB, the dominant source of the star's energy is coming from the hydrogen-burning shell. But when a helium flash occurs, the hydrogen burning nearly stops. This means, from an outside observer, the star's radius decreases during a flash, as well as its total luminosity, but its effective temperature increases. These shell flashes last longer than the helium core flashes, but not by much, as you can see by the slenderness of the spikes. When they abate, it's because, once again, that energy from the flash went mostly into lifting the electron degeneracy. Once that happens, gravity wins out and the hydrogen-burning shell reaches closer to the core, quickly redominating the total energy output. The star will then return to a new state that's close to its previous surface radius, luminosity, and effective temperature. But now, it's a bit more luminous and a bit lower surface temperature. After each flash, the luminosity starts at a lower point, again dumping helium ash into the growingly degenerate helium-burning shell. This repetition continues throughout the star's life on the upper reaches of the asymptotic giant branch. For stars slightly more massive than the Sun, say 5 or so solar masses, these thermal pulses create yet another deep convection cycle, which brings up carbon-rich material to the surface. This can be seen in the spectra of red giant stars. Notice in this sample spectrum that we're focusing on the visible wavelength bands, which are between 4,000 and 7,000 angstroms. Nearly all the emission is in the red end. This is typical for such carbon stars, where you see the banding absorption features due to numerous and varied carbon molecules, such as silicon carbide, in the star's expanded envelope. Carbon stars have recently become extremely important for cosmology. The tip of the asymptotic giant branch can be completely characterized by these carbon stars, making this part of the HR diagram a good standard candle distance indicator, as long as you have a large enough sample of stars in a distant galaxy. This physical process allowed a recent team, led by Wendy Friedman at the University of Chicago, to publish that the Hubble tension can be resolved by studying these stars using the James Webb Space Telescope's better resolution. But that's for another video. It's important to note that carbon stars are numerically predicted outcome of the stellar interior simulations of stars more massive than the Sun in their autumn years. These star spectra show evidence of stellar nucleosynthesis as predicted by these models. Now, these kinds of stars are very frequently variable stars, meaning they get brighter and dimmer through time. One known group of well-observed variable stars are called LPVs, or long-period variables. These stars are observed regularly by both professional and amateur astronomers. They range in pulsation timings between 3 months and about 2 years. The variable star named Mira, or Omicron Ceti, is one such star. This light curve is provided by the American Association of Variable Star Observers and shows the last 6 years of data. Most of these observations are visually by eye, either with binoculars or through a telescope. Mira can vary up to 7 magnitudes, and remember that a difference of 5 magnitudes is a difference of brightness of 100 times. So this star can vary over 100 times in brightness over about 300 days. Looking at Mira in ultraviolet and visible compared, we see that Mira's space velocity leads to an interesting self-interaction. I've alluded to the mass loss that can occur with these red giant stars, especially the AGB stars, during their thermal pulse phase. Mira's motion, combined with the mass loss, creates a bow shock. Since this outflow is principally composed of hydrogen, we see the Lyman alpha UV emission due to shock-heated gas. This motion is so fast that the hydrogen gas is ionized, and the emission is due to the recombination of the electron back into a hydrogen atom. Watch my video series on the interaction of atoms and light to learn more about this process. What Mira shows is visual evidence of the result of these thermal pulses. The outer envelope is ejected as a fast wind, and by fast we mean the star will lose about 10 to the minus 4th solar masses per year. That's 1% of 1% of a solar mass. The Earth is about 3 times 10 to the minus 6th solar masses, so such a star will lose about 100 Earth masses of material every year. For a 5 solar mass star, it'll take somewhere between 10 and 30,000 years to slough off everything above the core. For a star like the Sun, this means that it will lose 60% of its original mass out to space in a super wind. This wind will be composed of hydrogen, helium, carbon, nitrogen, lithium, and a lot of other elements that are pretty surprising. This mass loss will happen, as we saw before, in a series of about a dozen or so puffs, where the star's radius radically increases, leading to mass loss, followed by contraction and an even larger puffed-up radius. The last of the thermal pulses blows off what is left of the envelope over the course of a few thousand years. As the last of the envelope comes off, the hot carbon-oxygen core of our now-dead Sun-like star is unveiled. As seen from the outside, the temperature goes from 4,000 Kelvin, as seen in the envelope's gases, to 120,000 Kelvin, the supremely hot laid-bare core. However, the luminosity stays constant at about 3,500 solar luminosities. This incredible temperature of the bare core means that most of its emission is in the hard ultraviolet part of the spectrum, with even some soft X-ray emission for a while. These intense and numerous ultraviolet photons ionize the ejected envelope gas, forming a planetary nebula. For the next 10,000 years, the nebula is continually ionized and heated by this hot central core, blowing it and expanding it away to the space between the stars. The interstellar medium will now be enriched and changed by this infusion of processed material. The overall hydrogen content of the interstellar medium is thus infused with new helium, carbon, and oxygen, and all the other elements that are created in that star, which were dredged up and expelled. Incidentally, they're called planetary nebulae not because they're composed of planets or because one day their elements will go to seed future planetary disks around yet-to-be-born stars. They're so named because of the planet-like round shape of the nebulae, as observed by astronomers through early telescopes. William Herschel seems to be one of the first to coin the term in the 1780s because he thought these nebulae looked like planets. But the most definite use comes from the French astronomer Antoine Darquier de Palapoi in January of 1779. On a cold night, he described the Ring Nebula as being very dim but perfectly outlined. It is as large as Jupiter and resembles a fading planet. Just like so many astronomerisms, we know these nebulae aren't related to planets in a direct way, but the name is stuck out of a deep respect for history and an overriding desire to lightly annoy young astronomy majors and decidedly confuse non-English-speaking astronomers. Let's now take a closer look at some of these planetary nebulae. As we zoom in around the sky, the first thing we'll look at is the Dumbbell Nebula. The Dumbbell Nebula is located in the constellation Vulpecula, and it lives at a distance of about 1,360 light-years. It has the honor of being the first planetary nebula to be discovered by Charles Messier in 1764, and is the 27th object in the catalog that bears his name, which contains a list of things that are not comets, as per him. It's easily visible in binoculars, and it has a visual magnitude of between 7 and 8, and it's one of the favorite for amateur astronomers' star parties all over the world. I took this image using iTelescope's T18 scope using 3,000 seconds of stacked exposures in each of the RGB filters. It took only a little bit of simple processing to bring out these stunning colors. Astronomers at the National Autonomous University of Mexico computed its angular rate of expansion to be about 2¼ arcseconds per century. This angular size expansion, combined with the known distance, gives an age for this nebula of about 14,000 years. This would be an upper limit because of the angular orientation effects, but other groups have settled on it being about 10,000 years old. And if you look closely, you'll see the dumbbell contains these knot-like structures. These knots vary in appearance from symmetric objects, which sometimes have tails, to others that are really irregular and tailless. Their formation and the way they move and how they track through time depend intricately on how the star blew itself apart. At the center of the nebula, you can see the bare core, with about half a solar mass of material. The rest of the 4 or 5 solar masses of the star are in this nebula. And there's also a much dimmer component, here not visible, but shows up also as infrared emission. Now we're going to swing over to NGC 6302, also called the Bug Nebula or the Butterfly Nebula. This one is a bipolar planetary nebula in the constellation of Scorpius. It is one of the most complex planetary nebulae ever observed. The spectrum of NGC 6302, the Bug, shows that its central star is one of the hottest objects in the galaxy, with a surface temperature of over 200,000 Kelvin, implying that the star from which it formed was very large. The central star cannot be observed and is surrounded by a really dense disk composed of gas and dust, which you can see in the middle, and it makes it look like a pinched waistline for the nebula. This dense disk seems to have caused the star's outflow to be forced into this hourglass-like shape that you see. Just like many other prominent planetary nebulae, it's filled with ionization. We're in the form of walls and knots, and there's sharp edges to these lobes. And this bug is located approximately 3,400 light-years away, and the super winds from the thermal pulse AGB era, combined with the intense UV emission of the core, have accelerated the wind of material up to 600 kilometers per second. This amazing image was taken by the Hubble Space Telescope after the successful 2009 servicing mission and was a showcase image of that wonderful telescope's upgrade. Next on our tour is the Helix Nebula, which is located in the constellation Aquarius. Discovered around 1824 by Carl Harding, the Helix is one of the closest of all the bright planetary nebulae. The distance was measured by the Gaia mission to be about 650 light-years, well within the easy grasp of this parallax studying telescope. At this distance of 650 light-years, with an angular size of 25 arcminutes or half a degree, it gives a physical size of about 0.8 parsecs or 2.5 light-years across. With an expansion rate of about 31 kilometers or 30 kilometers per second, you can then make a good determination of its age to be about 11,000 years. Due to its unique appearance, you've probably already seen it or heard it called the Eye of God or the Eye of Sauron. Personally, I've enjoyed The Lord of the Rings since I was little, so I'm leaning towards Sauron staring at us. Again, you can see the core at the center of the nebula. It's worth just pausing for a moment and thinking about the fact that this core is not much bigger than the Earth, but yet its temperature is so high that its luminosity is incredible, and it can ionize all that gas all the way out to about a light-year in every direction. This means that if you traveled in a spaceship within about a light-year of this nebula and entered the gaseous wisps, your ship would be steadily ripped apart by the ultraviolet light coming from that core. Another name for my astronomy class is A Million Ways to Die, and this is one of them. Finally, in our tour, we go over to the constellation Lyra and view the Ring Nebula, M57, Messier 57. This is one of the great images by the Hubble Space Telescope. This favorite target for summertime amateur astronomers and early fall school star parties is a really tiny target in a telescope, being only about 1 arc-minute across. That's 25 times smaller in the same eyepiece than the previous Helix Nebula. Even though it's extremely far away, at about 2,600 light-years or about 800 parsecs, that places it only about 30% farther away than the Helix Nebula, which means it's much smaller than the Helix in a telescope then, not because of the distance, but because it's only been expanding for about 1,600 years. This is a much younger planetary nebula than all the previous 3. And what's fun about observing this nebula with a small telescope is using a special filter called an O3 filter, which looks at the specific wavelength of light that are emitted by strongly ionized oxygen in an extremely tenuous gas. The filter clearly shows the massive presence of oxygen. In this image, the bluish green is the oxygen, the reddish areas come from ionized nitrogen. These elements are commonly created in solar mass range stars as they climb the asymptotic giant branch. Coming back out, I've been talking about the cores of these stars illuminating the surrounding nebula. That core is a carbon-oxygen electron-degenerate gas that is now called a white dwarf. Typical white dwarf temperatures range between 8,000 and 40,000 Kelvin, and their sizes are about the same as our home planet Earth. Again, these nebulae are huge, spanning light years, and this tiny, tiny hot object is so incredibly fiercely hot that it's ionizing all that gas. As part of this ionization, when the freed electrons encounter an ionized atom with a free slot, the electrostatic attraction will grab that electron, and the electron will give up the energy of being captured in the form of light. The frequencies and intensities of the light tell us all about the composition of the star that created that nebula. We now see the star turned inside out, with all the material that was for billions of years trapped in the core now being flung out into space. This then is the final stage of our story of a sun-like star. The nebula has now fully dispersed, and the contracting carbon-oxygen core has become so dense that it is now a fully degenerate electron gas. Again, just like with the helium flashes, the pressure becomes independent of the temperature, so the pressure grows rapidly and soon counteracts gravity. The collapse halts when the radius shrinks to about Earth size, and we call this degenerate core again a white dwarf. For the Sun, deep in its future, the bare core will be about 40% of the mass of the Sun. Remember the luminosity equation, where the luminosity of a star is proportional to the surface area times and the temperature to the 4th power? White dwarfs are incredibly hot, but they're also really small. This means that their luminosity is tiny, and that means they cannot cool off with any great ease. The white dwarf that was the Sun will now begin a long, slow cooling phase that will last for nearly 1 trillion years as it fades away into a long night. But wait, the universe is only 13.8 billion years old. This means that not a single white dwarf that has ever been created has turned into a completely cooled off black dwarf. The universe is simply not old enough for a single white dwarf, or any white dwarfs, to have cooled off even to the temperature of the surface of the Sun. So every white dwarf that's ever been formed in the history of the universe still is a white dwarf and is incredibly hot and still emitting huge amounts of ultraviolet light. To learn more about white dwarf stars, see my lecture video series on that very topic. It's important to now look at an amazing result of all this stellar nucleosynthesis. As I described before, some really surprising elements do come out of low-mass stars dying on the asymptotic giant branch. Elements like strontium, molybdenum, tungsten, and even lead are copiously produced during the late AGB time due to the S-process nucleosynthesis. These elements are created in such stars by the excess abundance of neutrons created by all that carbon burning and oxygen burning. Since neutrons don't carry electric charge, they can easily interact with other nuclei. And if the total flux of neutrons isn't too great, meaning that the nuclei aren't getting hit by the neutrons too frequently, then these heavy nuclei, which are frequently radioactive, have a chance to decay into other nuclei before they absorb another neutron. This is why technetium 99 is seen in the spectra of older red giant stars. There are no stable isotopes in nature of technetium, which you can see lies in the middle of the periodic table, and specifically Tc99 is the most abundant isotope seen in the atmospheres of thermal pulse AGB stars, and it has a half-life of only 200,000 years. So this dredge-up that we've been talking about brings up truly deep material to the surface from very dense regions, which is then expelled out as part of these planetary nebulae. Most of the carbon and nitrogen and lithium in the universe was made in such dying stars. The carbon that makes up the DNA of your cells was made in some ancient star long since dead over 4.5 billion years ago. Oddly, most of the mercury and lead were also created in this way, as well as a good fraction of the silver and gold in your jewelry. So there's our evolutionary cycle for the Sun. As you can surmise, we will never see an individual star doing all of these phases. Our lives are simply just too short. How we measure all this is a combination of computer models based on all known physics, which must be made to match several things. First, the computer models that span a star's full life must be seen to match observed stars in the sky. The models must also predict roughly how many stars are in each phase of their lives. This means we need to sample huge populations of stars in the sky to see where they fall on the HR diagram. If the model predicts a huge amount of red giants, then the input parameters of the physics and the composition of stars must be tweaked to match the observations. And what exactly are these observations? I've alluded to the Hertzsprung-Russell diagram frequently and showed the evolutionary track of a single star around such a diagram. But the first best place to observe stellar evolution is in a cluster of stars. All of a cluster's stars are roughly the same distance, so their brightnesses can be mapped directly to their luminosities. For this famous double cluster in Perseus, we see a pair of classic galactic or open clusters. In this photo, we see a lot of bluish and whitish stars and only a tiny number of bright red stars. This is reflected in the HR diagram of these clusters. Most of the stars lie along the main sequence, and we see a turn-off point for the stars that are leaving the main sequence to become subgiant and giant stars. A few of the more massive stars have already become red giants. The numerical simulations based on all known physics point to these clusters having an age of about 10 million years. A much older cluster, Messier 80, is about 10 to 12 billion years old. The only stars on the main sequence are those stars with masses much less than that of the Sun. We see a lot of yellow and red stars in this Hubble mosaic. This is again reflected in the HR diagram. We see a lot of red giants and subgiants and a bunch of white dwarfs. In the discussion up until now, we tracked just one star of roughly a solar mass. But a cluster of stars has a huge range of masses. It is the mass difference between the stars that tells us where they are on the HR diagram. The more massive stars evolve faster and leave the main sequence sooner. 10 billion years is a long time, and so we should expect to see a lot of white dwarfs, which we do. It is these HR diagrams of clusters that give us huge amounts of information about the process of stellar evolution, which can then inform us as we wish to simulate the life track of a single star. If we then sum up the contributions of a huge amount of stars to a full population HR diagram, we get this. We're looking at an HR diagram of more than 4 million stars within 5,000 light-years of the Sun. This data is from the 2018 second data release from the European Space Agency's Gaia satellite. This satellite obtained parallax distances for all these stars, so we didn't have to rely on them being in the same cluster as previously. This local galactic neighborhood HR diagram shows the groupings in different regions due to differing masses, chemical makeup, and ages. It is the parallax which then gives us the absolute magnitude on the diagram. As you can see, the vast majority of the stars live in a region that's been named the main sequence, but we also see contributions due to red giants and white dwarfs. The other stages that I talked about are very sparsely represented because those stages are on cosmically short timescales. This HR diagram is the most important tool for all astrophysics, and it relies, amazingly, only on 3 parameters: the brightnesses in 2 filters and their parallactic distance. To learn more about how this comes about and how we actually do this measurement, please watch my video series, Cosmic Calibration: Properties of the Distant Stars. Next, as promised from the very beginning, what about really small mass stars? We define these stars as having less than 40% of the mass of the Sun. These stars, too, will be on the main sequence, or at least get there eventually, burning hydrogen into helium using the proton-proton chain at a cool temperature of 10 to 12 million Kelvin. But their low mass means they cook that fire on just the boundary of fusion, and so will last for nearly 1 trillion years on the main sequence. These stars will never get a degenerate core until the very end, when the entire star has been turned into helium and becomes a helium-only white dwarf. These stars will devour very slowly all of their hydrogen because they're fully convective and from the very core to the tip of the surface. These are the slow crockpot cookers of the universe. Their trillion-year lifetime means that there's not a single M dwarf type star that has ever died in the history of the universe. Again, the universe is only 13.8 billion years old, and these stars live to about 1 trillion years, which is 1,000 billion years. Even more interestingly, these stars make up about 70% of all stars in existence. But they're very, very, very faint and very underluminous. When we look out at the night sky, we don't hardly see any of these stars. All of the M-type stars that we see in the sky with either binoculars or a telescope are red giants. These tiny workhorses will be around long after the Milky Way has collided with the Andromeda Galaxy and all the hydrogen clouds in the universe have been used up to create other stars. In the deep, deep future, they will populate a dim universe with barely any stars in the sky. If some future astronomer in some young civilization looks out with some telescope into that dim void without any visible stars and finds a tiny fraction of them, his heresy to his contemporaries may very well exceed that of our Galileo. Well, that about wraps it up for the bottom 3 rungs of the life cycles of stars. I bypassed brown dwarfs because they never initiate nuclear fusion. They just keep collapsing and release their heat via the gravitational Kelvin-Helmholtz mechanism. Next time, we'll talk about the more massive stars. For stars much more massive than the Sun, they end in a far more dramatic way, and they occur in a far rarer number. Yet their explosions and the collisions of their remnants make up all the remaining elements in the universe other than hydrogen and helium. We saw how low-mass stars create many vital elements in their cores, but every other element in the periodic table comes about from these titanic stars and their interactions. Thank you for watching this lecture. I want to give a big shout out to my Patreon supporters and my YouTube members. Their support goes a long way to helping me deliver this content to you. I hope that you'll consider becoming a supporter. In any event, please like this video, share it around, and subscribe to my channel for all the latest updates and releases. Thanks again, and we'll see you next time. Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to talk about the exploding stars, the biggest stars in the universe. It's how they live, how they are born, and how they die. Again, let's go back and we can go back and look at the fiducial idea. The top area shows exactly how the Sun evolves from a protostar. It has a long main sequence lifespan of about 10 or 11 billion years. It swells up into a red giant, puffs off its outer layers of the planetary nebula, revealing the core as a white dwarf. And we see these things from the left-hand side, which is a star-forming region with a Horsehead Nebula in the middle. And then in the middle picture, we've got a globular cluster in the lower right and a beautiful open cluster in the open left, which is the remnant of a new batch of stars. And over on the right is the Ring Nebula, which is a planetary nebula surrounding a tiny, tiny, tiny white dwarf star that illuminates it and causes it to glow by ionizing. But that's a story for stars like the Sun that live about 11 or 12 billion years. We're going to look at more massive stars. Hot stars like O and B type stars, basically their masses are greater than about 4 solar masses. They burn extraordinarily hot. They live extremely fast lives, and they die very young. So their main sequence phase, they do burn hydrogen into helium in their cores just through a different process, not the proton-proton chain, but through the CNO cycle. They also build up a helium nugget in the core for their main sequence phase, because that's the definition of a main sequence phase, is hydrogen to helium burning. And they do this just like any other star. The main sequence is where stars burn hydrogen into helium. But for high mass stars, this lasts at most about 10 million or so years. So let's look at one of the more fiducial stars of this type in the sky. You know it by sight in the stars, but this is an artistic view of the star Betelgeuse. And Betelgeuse is a nearby supergiant red star in the constellation of Orion. And this is a beautiful piece of artwork by El Calzada at European Southern Observatory. And this is a wonderful picture by Babak Tafrishi of the constellation Orion above the Very Large Telescope Array down in Chile. And so what we see is the belt of Orion up there, and because we're in the southern hemisphere, Orion's inverted. So just above the telescope, the bright red star is the star Betelgeuse. And Betelgeuse, this is a picture, is a massive, not an artistic picture, but rather this is a massive array of pictures put together as a mosaic by Rogelio Bernal Andreu, and it was featured in Astronomy Picture of the Day in 2010. So Betelgeuse is the upper left shoulder of the giant of Orion. And there's all sorts of wonderful things going on in the Orion Nebula and the Orion area of the sky. But Betelgeuse is the star we're going to be talking about. Betelgeuse is a red supergiant star. It lies in the upper right area of the HR diagram with a spectral type of M and a luminosity of about 100,000 times that of the Sun. And it's about the same temperature as little red dwarf stars on the main sequence, or giants like Aldebaran, but it's much, much, much larger. And Betelgeuse is brighter, and we call it a red giant because it's brighter at red wavelengths compared to blue wavelengths of light. And so this is a sample type M-type star that we might get from I forget exactly where, I grabbed this from the Sloan Digital Sky Survey. And this particular thing shows an M-type star, and the wavelength band is from 4,000 angstroms to 7,000 angstroms, which spans the visible light. So to your eye, this is the part that is visible to your eye. And so I kind of grayed out the rest to the right. But you can see it actually glows a lot in the infrared. But for visible light, it's brighter in the red wavelengths than it is in the blue, and has striking absorption features and so forth. And because it's bright in the red compared to the blue, that's why it looks red in the sky. Now, we can also judge whether it's a giant or a main sequence star by looking at these absorption features of the dips from the continuum. You can imagine that this is actually some sort of continuum that goes over the top with lots and lots and lots of dips that go through. So where the peaks are is where the continuum is. So you could draw a line across the peaks of the continuum and then imagine that it's actually that the absorption lines are huge absorption lines down from the peaks, where the peaks go up to the continuum. And so you see they're very, very, very wide peaks, very wide absorption features. And if they're comparatively narrow lines, when there's only one or two, then it's called a giant star. And if they're wide absorption lines, then it's a main sequence star, because main sequence stars are compact. So therefore, they have a lot more Doppler broadening. The atoms and molecules are moving faster. So therefore, the widths of the lines are broader. And in a giant star, the widths of the lines are narrower because the pressure is lower. And because the pressure is lower, there's less movement of the atoms, and the atoms can only absorb it there near the frequency where they're absorbed. But if they have high pressure, they're moving faster, and so you can get Doppler shifts for the absorption. Anyway, so from the spectrum, which gives you the line widths, and the color, which gives you the temperature, you can deduce that this is a supergiant type star and of spectral class M. Now, how do we know it's really that big? I mean, what we can do is, remember, we can also take, if we have a handle on the luminosity, remember there's a luminosity relationship, or the Stefan Boltzmann relationship, where the luminosity is equal to the surface area times the temperature to the fourth power. So if we have a way of measuring the absolute luminosity of it somehow, and then we know roughly its radius, then we know its temperature, which is obvious from the spectrum, then we can determine its radius and determine it's an extraordinarily large star. And that's the Stefan Boltzmann relationship. Anyway, we do know that Betelgeuse is an extraordinarily rare star because it's a more massive star than the Sun. So roughly less than a couple of percent, like 2 to 4, like almost 3 or 4% of the stars in the sky are even as or could be as massive as Betelgeuse. Actually, more like about 1%. So Betelgeuse is probably much more massive than a 2 to 4 solar mass star. So we're really looking at the deep, deep, deep little blue sliver where we have a 4 to 8 or 10 solar mass type star, which is about 1% of all the stars in the sky, and Betelgeuse falls in that realm. It's not one of the small mass stars between 1 and 2 or a half or a quarter or less than a quarter the mass of the sun. It is in that elite category of very, very, very massive stars where so few of them in the sky are that massive star. Now, Betelgeuse is about 152 parsecs away, or about 500 light years, and the luminosity is about 120 times that of the sun. So it's extraordinarily luminous. And that puts it, this is really fun statistic. The absolute wattage is about 4 times 10 to the 26th watts. And if you compare that to what human civilization puts out, which is about 17 terawatts, we're nothing compared to the luminosity of Betelgeuse. We're nothing. 10 to the 14th times less. Oh my goodness. And the Betelgeuse itself is about 1,200 times that of the sun. That comes from both direct measurements, as we'll see in a second, as well as the Stefan-Boltzmann relationship. And we know that 100 Earths fit across the sun, but about 120 Earths fit across Betelgeuse. That means that it's bigger than the orbit of Jupiter. All right, so let's take some interesting looks. This is a 7 millimeter radio image taken with the Very Large Array down at NRAO, and it was taken in 1998 by Lim, Corelli, White, Beasley, and Marson. And they found that the optical disk of Betelgeuse is this roundish sort of thing in there. But the glow that we see here is a radio emission. Radio emission from Betelgeuse's very diffuse atmosphere. We see that Jupiter's orbit would easily fit inside of this atmosphere of Betelgeuse, and so Jupiter would slowly spiral in. And we see that another thing about Betelgeuse, it's not spherical. It's not a spherical star. So people thought, wow, that's really interesting, 1998. So following up, and prior to that, Betelgeuse was measured in terms of its physical size with the Hubble Space Telescope image of a direct imaging by Dupré et al. At Center for Astrophysics using the Hubble Space Telescope. And this is a direct image of Betelgeuse. We see that the star is actually quite large. It's much larger than Earth's orbit, much larger than Jupiter's orbit. So Betelgeuse is this enormous, physically large star. Now, a group at the European Southern Observatory took a series of images and then placed them inside using the VLT and infrared imaging as well as optical imaging to try to determine the actual dimensions of it. And if we take the little red dot that's in Dupré's image from before, it would just fit inside that red circle, just barely. And you can see that there's kind of plume-like structures that are visible in the infrared. Now, the right-hand side, this plumy sort of thing, is an infrared image. Remember these types, as we saw gently in the other spectrum that we saw before, that the vast majority of the emission from this star is actually in infrared. So because it's a cool, large star, and since it's cool, the dominant radiation is infrared. Well, it's also puffy. There's a plume shooting off to the side. There's also other plumes kind of noodling around. It's a really distorted thing, and it's not actually spherical the way we think of this, like the sun. The sun is spherical, but we can really think of Betelgeuse as not even spherical. It's just this pumpy sort of thing. And it's an incredibly sharp image. This was taken by the Very Large Telescope in Chile, which is that set of telescopes that we saw from Babak Tafrishi's image from before. And we're actually seeing this unknown plume to the right. What's funny is the individual pixels are as small as 37 milliarcseconds, which is about the same size as a tennis ball viewed from the ground at the International Space Station. And this is all near-infrared imaging. And if we then zoom out with a different infrared camera, again with the VLT at ESO, we see the black disk is the thing that is used to occult the star because the star is incredibly bright. It's one of the brightest stars in the sky. And so to actually get the image of material surrounding it, you need to actually block it out. And the previous image was put in the center, and the disk-like image that we see from Dupré's images is the red circle in the middle. And now we zoom out to show the full grandeur of Betelgeuse, which really doesn't actually seem like much of a star anymore. It seems like a star nebula thing sort of thing. And if you actually were to take a spaceship and fly over near Betelgeuse, you would find that you'd fly into this cloud-like structure that got brighter and brighter and brighter towards the center. You'd fly by globs of mass that's moving out with enormous winds that would buffet your spacecraft as you tried to get closer and closer. And eventually you'd find yourself in an incredibly bright, foggy mist and get closer and closer to the star. And you would just all of a sudden be close to what would be bright enough that we would call the photosphere. So many of the absorption features that are found in Betelgeuse's spectrum come from this expanding shell of gas that comes off of the star itself. So Betelgeuse is shedding a lot of mass. And just like we saw last time in the low mass stars, how we had a star like the sun puffs itself apart and forms a planetary nebula, Betelgeuse isn't waiting. It's not done yet with its life before it starts really puffing itself apart as all high mass stars do. And that means because it's puffing and moving, it's variable. So it's an actual variable star, which is easily seen with binoculars. So if you want to go out in the night sky and take a pair of binoculars and see what the variation in magnitude is, this has come from the American Association of Variable Star Observers. This is their data, and it's compiled by a number of observers. And these observers then submit their data to the AAVSO. You can become a member too. It doesn't cost you. Well, it costs you a little bit, like $20 a year. But then you get to submit your data into this set, and you can make meaningful science measurements just with binoculars, specifically of this star. But as you can see, the star varies as time progresses from left to right. We see that the brightness and magnitudes varies pretty big. It can vary up to a magnitude in brightness. As you can see, roughly about 2008 or 2009, it was pretty dim, and then it brightened it went as dim as magnitude 1, and by about a couple years later, it was as bright as magnitude 0.01, almost a zero magnitude star, and it's been brightening and dimming by a quarter of a magnitude fairly regularly as it puffs itself apart. So Betelgeuse is an extraordinarily variable star, and it's fun to observe. So I would invite you to use this as one of your primary variable stars if you want to observe them and do some science in your own home. This is a great way to do it. And you can learn how to do this by going to the American Association of Variable Star Observers. You don't have to become a member to submit your data, but they always appreciate that you do. All right, so stars themselves can be extraordinarily big, as we've seen in the past. The sun is only about 700,000 kilometers across. And so on this image, it's really tiny. And the bright star Arcturus, which is in the constellation of Bootes, is much, much, much larger than the sun, almost 20 times larger, 30 times larger. About 30 times larger. And if we then look at the red supergiant Antares in Scorpius, it's extraordinarily large, larger than the orbit of Mars. And so these are the red supergiants. So red supergiants exist like Betelgeuse. So how do they live? Well, they're so big, they're so massive. So a large physical star like a red supergiant doesn't mean it starts like that. It started as a main sequence star and swelled up. But while it was on the main sequence, it burned hydrogen to helium. But it does not do so. But these massive stars, any star more massive than about 4 times the mass of the sun, does not use the proton-proton chain to fuse hydrogen to helium. It uses the CNO cycle. It does fuse 4 protons. You can see the equations. These are a set of reactions. Where a proton, P, combines with a carbon-12 nucleus, they collide together. And the arrow says the output is a nitrogen-13, or a light nitrogen nucleus, and that emits light in the form of a gamma ray. That's what that little YE sort of image is. That's a gamma ray. The next step is this light nitrogen nucleus. Then beta plus decays, which means that one of the protons turns into a neutron and therefore emits a positron and a neutrino. This can only happen inside the nucleus of an atom. It can't happen as a free proton, but there it is. Of course, then the positron interacts with an electron to form a gamma ray as well. But then the carbon-13 then collides rapidly with another proton, which forms nitrogen-14. So we're back to nitrogen again, and that emits light in the form of gamma rays. And then that nitrogen gets slammed by a proton and it forms oxygen-15, which itself is radioactive and unstable, falls apart to nitrogen-15, which is briefly stable. And that emits, again, another positron and a neutrino. And then that gets slammed by another proton. And that forms the chain, which returns it back to a carbon-12 nucleus, and that spits out a helium nucleus. So we can add all this stuff together. Basically, 16 objects, so the proton could be something about 1 in the upper left. So 16 things go together to make a carbon-12 and a helium. But notice that the carbon-12 acts as a catalyst. It returns back to the beginning of the cycle, having been used up, and the intermediate processes of creating nitrogen and oxygen along the way. So it doesn't really go anywhere. So it acts as a catalyst. And that catalytic reaction keeps the carbon going, and this is an incredibly important element. So for the sun does a little bit of this. About 2% of the sun's output comes from this. But once you get above 1.1 solar masses, or just a little bit more massive than the sun, CNO is about 50%. But once you're up to about 4 solar masses, it is 100%. So by 2 solar masses, you're doing a CNO cycle completely. Now, this is, of course, inefficient, but it's really interesting to return to the idea that what does fusion energy give you? Remember, when you fuse 1 gram of hydrogen into 0.993 grams of helium, it loses mass. Some of the mass of the 4 hydrogen nuclei, those 4 protons, gets converted into energy. Less than 1%, about 0.7% of a gram gets converted into energy. And for every single one of those things, that provides 6 times 10 to the 18th ergs, which is a large amount of stuff. And that's a huge amount of energy by comparison. Just to do this one interaction, that was enough energy to lift about 30,000 tons, 64,000 tons of rock up to a height of 1 kilometer. So basically, just fusing 1 gram of hydrogen into helium is enough energy to take a building and throw it into the air about 1 mile. That's what fusion energy gives you. So if someday we can figure out how to do this safely and efficiently, we could replace pretty much all of our energy needs with fusion if we can figure out how to do that, which would be pretty cool. Anyway, so just like low mass stars, no party lasts forever, and every star, no matter what is big or small, population 1 type stars, which are young stars that have come through reprocessed material, have roughly about, by abundance, is about 10% by numeric abundance is helium, but then about 90% by abundance, meaning the number of particles, is about 90% of the particles are hydrogen. And about 5 billion years into its life, the sun has only converted about 10% of its hydrogen in the core into helium. And by about 10 billion years, the sun specifically, now we're not talking just going back to the sun just to get reference frame, the sun will have converted all of the core material to helium, and a significant fraction, out to about half the star's core, will be helium. Now, that's what happens in the sun. A very similar thing happens in every main sequence star. It builds up this nugget of helium in the core, and when that runs out, it's over. And it doesn't matter whether it's using the proton-proton chain, which is the upper left, or the CNO cycle, which is the upper right. Those are the 2 dominant ways that hydrogen gets fused into helium inside of stars on the main sequence. That's the way it's done. There's other things then will come later, which is the triple alpha process. We described that when we talked about the sun, when the sun started dying, and that happens too. But even that doesn't last. Helium fusion doesn't last because you run out of stuff too. Anyway, so what will happen to a massive star that is way up the main sequence, that's an O and B type star, when it starts to run out of fuel and it uses up its hydrogen in the core? Once it's exhausted, it does the same dance that the sun would do. The inert helium core contracts down and starts heating up. There's, again, the hydrogen burning shell around it and around that contracted core, because pressure, gravity pulls the star together, and it just gets compressed and hotter, but it's not participating in fusion because it's not hot enough yet. So hydrogen burning or hydrogen fusion is in the shell around that nugget in the core. And then this huge puffy envelope gets to expand. So these red supergiants, unlike the sun, which just kind of lazily goes up, no, these shoot straight across to supergiant phase, and they get enormous, radically enormous in a very short period of time, less than 1 million years. Now, the funny thing is, along the main sequence, stars don't have a huge radius difference. Pretty much an O-type star in the main sequence is just only a little bit bigger than the sun on the main sequence. The radius isn't that much bigger. But once a massive star runs out of hydrogen, it swells up much larger than the sun will ever get. The sun will never become a supergiant, it'll become a giant star. But these stars become supergiants. Eventually, the star, this supermassive star, gets the core temperature raises to about almost 200 million Kelvin. That's enough to start up helium burning. And helium burning through the triple alpha process, as we showed before, that makes carbon and oxygen. That only lasts, we're in the sun, this would last about 1 billion years. For massive stars, it lasts about 1 million years or less. And then we've got this layering set that happens down in the core where there's helium burning in the core, then there's hydrogen burning around. And notice that there's no helium flash, because now it's going to be there, when it ignites it smoothly. Stars more massive than about 2.5 times the mass of the sun don't have a helium flash, meaning the star never, the electrons do not get so compressed in the core that they become degenerate. And the degeneracy never occurs for stars more massive than 2.5 times the mass of the sun. And it starts burning very, very, very gradually. So much more massive stars simply wag back and forth, and they get bigger and smaller, hotter and cooler, and they stay at that extraordinary luminosity, but their surface temperature changes. Now remember, the HR diagram shows the surface temperature. So the surface temperature of a supergiant star ranges between, say, 3,000 Kelvin and maybe 20 or 30,000 or 10 to 20,000 Kelvin. That's a blue supergiant. A blue supergiant isn't really that blue. It's more whitish because it's kind of the same temperature as an A star. But I guess an A star is kind of bluish. It would be bluer than the sun. In any event, it becomes a blue supergiant when the helium ignition starts, and then it smoothly moves back into this new framework. So that's producing more energy, which is producing a little bit more luminosity, but that allows the star to actually collapse back down. All right, so when the helium finally runs out in the core, and that doesn't take long, it takes an extraordinarily short period of time. In fact, it doesn't get down to the horizontal branch at all. It just kind of wags back and forth. When it runs out of helium in the core, then the carbon and oxygen core collapses and heats up. And that's a big deal because now the hydrogen helium are burning in shells around it, and it becomes a supergiant again. So it does this whole dance all over again. Notice how the size of the star is dependent upon what's happening down in the core. When the star grows in size, it grows in luminosity. And it's growing in luminosity because the energy output that must occur is getting very, very, very high in the core because there's no new energy source. It's contracting under gravity. It's running out of fuel. The atoms and molecules, they're not even atoms. They're just ions. The nuclei have to move insanely fast in order to find other nuclei that they can fuse with, because they're running out of sources of things to hit. So therefore, the temperature has to rise. When the temperature rising means that the particles are moving faster. And they have to move faster because they have to go farther in order to find something, in order to make the fusion. So that's kind of what's happening. So eventually the carbon-oxygen core continues to collapse. It gets smaller and smaller, and that releases more heat by gravitational collapse, because as you collapse a gas, it releases the heat. And eventually the core temperature exceeds 600 million Kelvin. And then the density is insanely large. It's about up to 150,000 grams per cubic centimeter, which is 1,000 times more dense than lead or gold. So a typical gram, a cubic centimeter of gold might weigh a kilogram, but this star, which is a gas, will weigh 150 kilograms per cubic centimeter. And it's still a gas. It's just really bizarre. It's not a solid, even though it's much more dense than lead and gold, 1,000 times more dense. Finally, we can get to the point where carbon fusion can occur. And then we get all sorts of reactions. Carbon burning is a new set of reactions that happen for much more massive stars that are much more massive than the sun. Carbon can slam into another carbon nucleus, and that forms magnesium. Neon can slam into helium, and oxygen can slam into two helium nuclei, and that builds up an oxygen neon magnesium core. Now, the oxygen neon magnesium core is also inert because it's not hot enough to fuse oxygen into anything heavier than that. And so carbon 12-12 fusion creates the products of magnesium or neon and helium or oxygen and helium. Those are its byproducts when carbon 12 smacks into another carbon 12. This doesn't release a lot of energy because, remember, it takes a lot of energy to make them initially, and each larger nucleus that you get gives off less and less energy. So you got to do more of it, and there's less of it to do. So you have to do more of it. There's less of it to use because now we're knocking together fewer objects because they're all combined together, and you get less energy out of it. So this can't last long. And so the reaction rate must be higher so that it can stay, so the star can stay aloft. So carbon burning can only last about 1,000 years before it runs it out. And that's roughly where Betelgeuse is now. We think that Betelgeuse will one day explode in a supernova, which I'll talk about later and next time, but it might be within the next 1,000 years or 10,000 years or a million years. So where Betelgeuse is now, it has an inert oxygen neon magnesium core. Very rapidly, there's a carbon burning shell happening fantastically quickly around it. Above that it's hot and there's nothing in there except that. The helium then mixes through, and that creates helium burning in the shell around that, and whatever protons are left that are just on the boundaries of that burn and fuse hydrogen into helium. So the helium burning shell makes helium, which descends into the helium burning shell, which makes carbon, which descends into the carbon burning shell, which then when the carbon burning creates oxygen, neon, and magnesium, which descends below. And all above the supergiant envelope, it's very, very, very unstable below. It's puffing off its outer layers, just like we saw initially with Betelgeuse just puffing itself apart, because the interior is an extremely violent place. So carbon, oxygen, neon, magnesium core is about what stars between the masses of about 4 and 8 solar masses will ever do. That contracts and contracts and contracts. That core of oxygen, neon, and magnesium contracts, and that contraction releases even more heat, and that pops and creates those shell burning around it, which is incredibly unstable, which pushes the star apart and makes it froth. Now, these are the low-end masses of stars that will end up making what we call Cepheid variable stars. Cepheid variables run between about 5 and 20 solar masses, and Cepheid variables will become incredibly important when we study the Milky Way and we study how we can find the distances to the cosmos. So these are the progenitors, and this is the time of life where some of these massive stars become Cepheid variables, when they pass back and forth into the upper left area of the HR diagram above the main sequence. So these kinds of stars eject all their stuff, just like we saw Betelgeuse doing, and they leave a white dwarf behind, just like we saw with the sun in the previous thing. So a massive, super heavy-duty stellar wind coming off and leaving a core behind, a white dwarf core with a large planetary nebula. Much more massive than that, at least 8 times the mass of the sun. Then carbon burning can happen. The carbon burning evolution is insanely quickly. It'll happen less than 1,000 years. And the star's envelope has no time to respond to that. And there's a big thing that's going to happen really soon. However, there are incredible, strong stellar winds that can be shown, that are evident from these massive stars, and they can erode the outer envelope, pushing it outward, making enormous bubbles and burbling appearance to the star. And Eta Carina, which is one of the great examples of such a massive star, a star much more massive than 8 times the mass of the sun. I believe that Eta Carinae is about 20 to 40 solar masses. And we see from this Hubble Space Telescope image of the nature of this particular star, which is Eta Carinae, which is clearly undergoing some violent stuff. These bubbles demonstrate that the star is incredibly variable. It's puffing off its outer layers incredibly violently. And this can't last, of course. And so this star is in the course of dying, and very, very, very soon it will do something very catastrophic. And one that, when Eta Carinae finally goes supernova, you will be able to read by it at night. So for much more massive stars, the oxygen neon magnesium core contracts and contracts, and by contraction it releases gravitational energy, gravitational potential energy, then heats it up to 1.5 billion Kelvin. I mean, how do you even get past what that is? Okay, I really can't give you a handle on what 1.5 billion Kelvin is like, but let's just say it's bloody hot. And the density is now about 10 billion grams per cubic centimeter, or 10,000 kilograms per cubic centimeter. These are extraordinarily rare conditions. Remember that massive stars, extremely massive stars, make up the most rare of all of the stars in the cosmos. So even though they're incredibly bright, they're quite rare, with far fewer than 1% of the stars in the sky will ever do this. So neon, I'm not going to really go through all the reaction rates because now they get extraordinarily complex. And when neon burning occurs, it will create more oxygen, more magnesium, and lots of other heavy elements. Now we're below the element iron. Now, a lot of these reaction networks, remember the carbon, nitrogen, oxygen created neutrinos, as well as all of the carbon burning that created the oxygen, neon, magnesium, that created enormous numbers of neutrinos. And now most of the luminosity of the star becomes in neutrinos itself. And the star rapidly creates this core, and neon burning can only last a couple of years before it runs out. But neon does not provide, it provides even less energy than the previous step. And so there's fewer particles, it provides even less, the temperature is even higher, so the reaction rate is even faster. Neon is done in a couple of years. When you're done with that, well, what the heck? What's next? Well, you burn oxygen. Oxygen then starts fusing, and the temperature rises rapidly into about 2 billion Kelvin, and the density rises even higher in the core. Remember, this is still a gas. This is still a gas, and it's still gaseous because the temperature is so high, even though it's almost 10,000, 20 or 30,000 times more, 10 or 20 million times more dense than water, and 10 or 20,000 times more dense than lead or gold. But this temperature finally allows oxygen to be fused into silicon, sulfur, phosphorus, and pretty much everything up until iron. Now, most of these reactions have enormous numbers of neutrinos because there's all sorts of, many of the reactions create huge numbers of neutrons, which then decay rapidly. These rapid decay as neutrons then get captured and also create neutrons as well. So there's multiple different reaction processes that are happening in the star. I'm not going to really talk about the S process or the fast process or slow process, the RRS processes, because that gets even more complicated. But suffice it to say that the star, in these last days, the neutrinos losses are much more, there's more energy coming out of neutrinos than there are in light. Now it's building up a silicon core. So silicon is now building up, and this lasts for about a year. Finally, oxygen runs out. The silicon core contracts, and it heats up till it goes even higher in temperature and even denser, over 100 million times that of water, the density. And finally, when silicon burning occurs, the temperature is so incredibly hot that the silicon itself cannot withstand the intensity of the light that's there. The photons are so incredibly energetic at this temperature that they actually break the silicon apart into helium again and back down to protons and neutrons. So the silicon's getting destroyed by the light. And then the rest of the silicon is fusing into nickel and iron. That doesn't decay yet. This builds up an enormously heavy nickel and iron core, which will last only for about a day. So the temperature of the star, the luminosity of the star is incredibly large, but yet it only lasts a day. And here's nearly our finishing picture. At the end of this life of this supermassive star, more than 8 times the mass of the sun, there's hydrogen burning shells, helium, carbon, neon, oxygen, silicon, and all of these fusion shells where each layer is raining material down on top from above down below as the pressure pushes it in. But yet down in the core, there's an iron nickel core, which is doing nothing. The size of the expanding envelope due to the instabilities happening down in the core is now bigger than the orbit of Jupiter, just like we see Betelgeuse being. And the reason for this iron nickel problem is what we call the nuclear impasse. Now, why are we caring about this? This is what's going to happen. This is why there's a big, 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 big problem. When you fuse light elements together, you release energy. You release energy in the form of light, and you release energy in the form of neutrinos. But iron is the most tightly bound of those things. So you get energy by fusing light elements into heavier elements, so long as the elements are lighter than have an atomic number
less than 26,
which is iron. So they release energy. But if you want to fuse elements heavier than iron, it must absorb energy. So once an iron core forms, there are no fusion reactions left for the star to tap in order to release energy. So gravity's still working, and that's what's happening. And here's a view of that thing again. Below iron, fusion will give off energy. Above iron, fusion takes energy, or more specifically, fission gives off energy. So that's why we use uranium in order to power our nuclear power plants, because uranium falls apart. And as it falls apart radioactively, it gives off energy. And that's what the far right-hand side shows. But we're talking about stars. We're talking about massive stars. And they all try to go towards iron, because iron is the most bound of all the nuclei. And if we look and zoom in really close to this binding energy, we find that it's specifically iron 56 and nickel 56, which are the most bound nuclei of all. And we see that this reaction network shows how much energy you get out, with the largest jump in energy coming from hydrogen up from on the far left-hand side. When you start with hydrogen fusing to helium, that's the biggest step. When you fuse helium into carbon, notice the step from helium-4 to carbon-12 is really tiny. And then the step from carbon-12 to oxygen-16 is small too, but is much smaller. Again, from oxygen to neon, it's a teenier step. And so each step is smaller and smaller and smaller until you get to iron. So each step of this fusion reactions gives off less and less and less energy as it goes, until you get to iron, and then it takes energy in order to fuse it, because that's what the curve means. So that's the end of the road. At the end of the silicon burning day, there's just an inert iron core with some nickel in there too, and there's this huge onion skin of burning shells all around it. And very soon, the iron core exceeds about 1 to 2 solar masses and begins to contract and heat up. And what it does at the end is final, catastrophic, and amazingly bizarre and wild. That's the end of the road for these stars. And stars between masses between 4 and 8 times the mass of the sun, they burn all the way up to carbon. And anything less than 4 solar masses only burns helium. And the cores of these intermediate mass stars become white dwarfs. Anything bigger than 8 solar masses gets all the way up to iron and does a catastrophic collapse. And what happens then, we'll talk about next time. See you soon.
Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be talking about supernova. And supernovae are exploding stars, supermassive stars that are at the end of their life, and they go out with a bang. So let's see how they work, because we talked about large stars and how they lived last time, and we found that they actually don't live as long a lifespan as low-mass stars. So let's see what the big boys do. So the endpoints of various stars of solar mass levels is kind of summarized here. This comes from one of the Pearson-type textbooks. And if it's really small, less than 8% the mass of the sun, it does not do anything dramatic. It becomes, they're brown dwarfs. And they basically do not, they never initiate hydrogen fusion. Between about 8% of the mass of the sun, about a quarter of the mass of the sun, the final end state would be a star that has completely converted itself from hydrogen into helium, and it becomes a helium white dwarf. Somewhere between, say, about a quarter of the mass of the sun and about 4 to 8 times the mass of the sun, this table I think is a little bit old, the star ends up as a white dwarf, a carbon-oxygen white dwarf. And if it's much, much larger, then about 4 to 8 times the mass of the sun, about 12 times the mass of the sun, at the time of main sequence burning, then it'll end up with a neon oxygen white dwarf. And if it's larger than that, with 12 solar masses, you get a supernova. And a supernova doesn't produce a planetary nebula or a white dwarf. It produces something completely different. So let's see what that looks like. Last time we talked about the last days of a supermassive star, and where we ended it with, where massive stars go through these in huge, fast burning. Burning now means fusing hydrogen into helium or some element into another element to liberate energy. And very massive stars, roughly at least 8 to 10 times, at least 10 times the mass of the sun, they burn hydrogen into helium for only about 10 million years, a very short time period compared to the sun's 10 billion year rough lifespan, which is about 1,000 times longer. And once they do that, they only burn helium for about 1 million years, convert carbon into oxygen and neon for only 1,000 years, fuse neon into oxygen for only about 10 years, oxygen into silicon only for about a year, and then the final stage of burning silicon into nickel and iron only lasts a day. Now this means that down in the core of this nested onion skin sort of thing, way down in the core, a very, very large inert iron and nickel core is building up rapidly and compressing and starting to do a major compression, as it's not producing any energies, but it does release energy by compressing. So it's releasing some of its heat by simply releasing it through gravitational compression. And that's what the iron core is doing. So at the end of this day, there's all this shell burning, and we've seen burning again here means fusion. Hydrogen fusion, helium fusion, carbon, neon, oxygen, silicon, and fusion all the way down into the core. The exterior of the star is now extraordinarily massive. It's a red supergiant or a red giant or maybe even a blue supergiant, but it's definitely a supergiant star. And the size of the star now has expanded out to about 5 astronomical units, or almost the orbit of Jupiter or larger. But the core is extraordinarily compact, and that's where all the action is. The outer envelope is just primarily hydrogen and helium, but there's practically no mixing between the outer envelope and the inner core. So we gotta really, now we have a touchstone that we have to actually understand for what's gonna happen next. And what we've really been talking about the entire time is how much energy is liberated by combining nuclei together. And that's what we call the binding energy per nucleon. And this graph, which comes from data that I downloaded from the International Nuclear Structure and Decay Data Network, which is a subdivision of the International Atomic Energy Agency, which governs, which tries to help people not explode nuclear weapons in various countries and so forth. It's one of the things they do. Anyway, they do have a very fascinating set of data about the nature of atomic energy and nuclear energy. And so I downloaded all the data and found how the binding energy per nucleon is in mega electron volts, which is a little tiny amount of energy, but in terms of nuclei, it's pretty large. The number of nucleons on the bottom shows how many protons and neutrons there are in the nucleus. So those were the nucleons we're talking about, protons and neutrons. And notice the graph has a peak right around 50 or 60, right? Just north of 55 or 60. And there's some other residual peaks off to the right, and there's a big drop off to the left. Everything that we've been talking about with the little stars up to this main sequence stars takes tiny nuclei, which would be on the lower left with number of nucleons. 1 is hydrogen, which is a proton, and the number of nucleons builds from 1 up to 4. And in fact, I'm just going to move my mouse across and show you where helium is. And right there, where I put my helium, where I put this on there, that is helium. Helium nuclei are incredibly well bound. So if you put helium to get hydrogen together to helium, you get a big jump. So there's an enormous, enormous jump that happens when you bind hydrogen into helium. All right, so this graph shows how much energy is liberated when you put all these protons and neutrons that into a nucleus, or how much energy you have to provide to the nucleus to tear them apart. So it's interesting to note that this graph has a peak, and it drops off to the right for very, very large nuclei, and it drops off to the left for very small nuclei. So this means that we will have what's called a nuclear impasse. The fusion of light elements, anything less than iron, gives off energy due to fusion. So we see in this graph below that hydrogen, or H1, which is just a proton, gives off energy by fusing hydrogen to deuterium, H2, which we see down below. And that's what we've known that, though, since we talked about the proton-proton chain. And we also knew that hydrogen fusing to helium gives off a lot of energy, because there you see He4 in this graph, and that gives off energy. We also know that fusing helium into carbon gives off energy, but not as much. See the difference in energy between helium-4 and carbon-12? It's not as much as the difference between hydrogen-1 and helium-4. There's a large amount of energy that's given off by fusing hydrogen and helium, but not as much from helium to carbon, and the step is even smaller from carbon to oxygen. In fact, if you look, you can see that as you go up and up and up to the peak at iron 56, that each step is progressively smaller. You get less and less and less energy out of the reaction by combining something with carbon-12, combining it with a helium nucleus to form oxygen-16. You don't get as much energy. In fact, the energy difference to get it from oxygen-16 to iron 56 is very small. So therefore, there's less. This is what we were talking about in the last time, is as it progresses, each successive step provides less and less and less energy output. It also takes more energy to do it because these things have protons, and the protons push against each other for the electrostatic force. And so you get less and less energy out. The nuclei are bound less and less strongly, which means it takes less and less energy in order to rip them apart. And if you fuse but the general trend of this whole graph is that if you fuse elements lighter than iron together, you do get energy out. And if you have to get elements heavier or more massive than iron with more nucleons in the nucleus of the nucleus, then it actually has less bound. So if you look at uranium-238, we have on the cross there, we on the right-hand side, we see that it is less bound than iron-56, meaning it has less binding energy per nucleon. And so just piling stuff on top of it means it takes energy to put these things together in order to actually create uranium-238. You don't liberate energy, you absorb energy in order to go there. We see that helium to carbon gives off energy because you go up. Carbon to oxygen gives energy because you go up. And oxygen all the way up to neon, and magnesium all the way up to nickel gives energy all the way up to iron-56. And below that, fusion gives off energy. But if you fuse elements together and try to go more massive than iron, it takes energy because the binding energy is less, so you have to push it together to keep it together. That's a better way of talking about it. In fact, another way to look at it is we use uranium in our fission nuclear reactors in order to get electric power, and we get that power by uranium radioactively decaying down to lead, and that gives off energy. And so uranium decaying to lead, which is about halfway up, or more than halfway up that from the far right-hand side to the left towards the peak, gives off energy. So above iron, fission gives off energy. And to get things more massive than iron, it takes energy. So this is a more detailed view. And I was poking around on the internet to try to find a little better view, but this is not very clear. And what I did then is I decided to try to zoom in and show you what's really there, but it's really not clear. We've got iron 56 and nickel 58 at the top. We have strontium 6088 and scandium and cesium, and there's polonium, lead 208 way down there. But these graphs are kind of hard to read. I'll grant that because they're low resolution on the internet. So again, I went back to the IAEA website and grabbed just that data to see what the most bound nuclei are. And we'll look at the top peak. We see there's three nuclei that are the most bound. And iron 56 is the leftmost of the three top ones. Nickel 58 is just a little bit more bound, and then there's nickel 62, which is also just a little bit more bound than nickel 58. So anything below this peak, you get energy by fusing things from the left-hand side of the peak up to the right-hand side of the peak. And the typical fusion means take an element, take a nucleus, and either slam a proton into it or slam a helium nucleus into it. That tends to be the dominant reaction that you would do in order to do fusion. You sometimes have like two carbon nuclei slamming together, and that falls apart and gives off stuff. But it's very easy to say, let's get a helium nucleus because it's lighter than a carbon nucleus, and spin it up really fast so they can smack into stuff. Be that as it may, however many ways there can be, because each one of these dots is a separate nucleus. So there's lots of different nuclei, lots of different isotopes of various nuclei. But you get them by doing fusion or then radioactive decay by fission. So what happens in the center of a star? In the center of the supermassive star, the iron core is going to grow and grow until by the silicon fusion happening above it, until the mass becomes about somewhere between 1.2 and 1.4 solar masses. And then the core will collapse under its own mass because it exceeds the Chandrasekhar limit for it exceeds the limit that a white dwarf can have before it will explode. So a white dwarf is basically forming an electron degenerate core in there. It can't be supported by electron degeneracy. And all of a sudden, the core collapses down rapidly and heats up amazingly. And it gets up to about 10 billion Kelvin, and the density is about 10 billion grams per cubic centimeter. So one sugar cube would weigh 10 million kilograms, or that roughly translates into a few 100,000 tons. So we have a sugar cube weighing hundreds of thousands of tons. That's a lot of weight. And that's how dense the core becomes. However, even though it's that dense, it is still a gas because it is so incredibly hot. And way down in the center, it's incredibly turbulent because the star's core is rotating, and as it rotates, it spins everything around, and so you got all this crazy mixing happening. And even though the core is there, it's not moving. It's the star itself is spinning. When it's that hot, the energy is primarily in the form of kinetic energy of the nuclei bouncing into each other, and that's at roughly the same temperature as the light. So there are gamma ray photons that can't go very far because the density is so incredibly high that they actually equalize the temperature with the material around them. So everything is the same temperature, both the light, the profile of the light in the black body spectrum, as well as the nuclei that are zipping around. And that has a number of results. Once you get enough of the energy in the form of light, then the light itself has enough energy in form of a number of mega electron volts to actually disintegrate the nuclei. Remember, those nuclei have binding energies of iron is roughly about 8.5 or 9 mega electron volts. And once the temperature of the center of the area exceeds about 10 billion Kelvin, which is really high, that's 10 billion, right? 10 billion. Once it exceeds that, then a significant fraction of the energy of the light actually has an energy on the order of about 10 or so mega electron volts, which is a very high energy gamma ray. So once these gamma rays go flying around, they can actually disintegrate the iron nuclei. And when the iron nuclei disintegrate, they absorb the energy of the light. And then that lifts the nucleus apart, giving the constituents its energy. And that binding energy then is absorbed out of the system. And so as as the nuclei now start to absorb the light and then break apart because of it, this is called photodisintegration, it removes the light and therefore removes the energy that supports it. It robs the core of energy. It robs the core of pressure because if it's hot, it has high pressure. Second, then the density continues to increase, and at this, because as everything's breaking apart, then there you have free neutrons and free protons. So as there's photodisintegration happening, it doesn't just break it into helium nuclei, it breaks it down into also protons and neutrons. That's very high energy light. And so now the protons and electrons are very close together. They can fuse together to form neutrons. And the neutrons then, of course, give off neutrinos. And neutrinos carry a tiny amount of energy, and as they carry a tiny amount of energy, they escape, and they just leave. Because neutrinos don't see anything. Remember we talked about the surface of the sun, deep, deep, deep in the core of the sun, where neutrinos just escape. The reactions occur in the sun, and they don't even see anything. So the neutrinos get out of there, taking energy further away from the core, leaving it with no energy. So there's no energy to provide pressure against gravity, because remember, gravity is always working. So the neutrinos escape, carrying away more energy to provide the pressure, and then it collapses catastrophically. So right around this only lasts about a day, this whole event. And once the iron core starts to collapse, it begins at about something roughly the size of the Earth, at a density of and the iron core collapses at about 100 million grams per cubic centimeter. And then a second later, this is almost free, it's faster than free fall. Actually, it is free fall given the gravitational pull that it is. In total free fall, it drops from 6,000 kilometers in size down to 50 kilometers in size in less than a second, at about a quarter of a second later. And then the density increases to almost 10 to the 14th grams per cubic centimeter, which is astonishingly high density. And that density is the same density as an atomic nucleus. So you can't really push the nuclei together anymore because now they're literally in contact. So the density raises in the core, and it has to stop because now neutron degeneracy comes into play, just like we talk about electron degeneracy in the center of the sun. That causes the helium flash in low-mass stars. But with neutron degeneracy, that then says, I'm a neutron, I can't go on top of another neutron, I can't go inside another neutron, we can be right together, we can be next to each other, we can touch each other, but we can't be inside each other. So therefore, the neutrons don't have any place to go except stack up against each other, and they cannot compress anymore. So since they cannot compress, basically it makes a bounce. So then you have an enormous bounce off the core because material still is piling down on top of it. The core is now collapsing down to about 2.5 times 10 to the 14th grams per cubic centimeter, which is the density of an atomic nucleus. And the strong nuclear force now comes into play, which does all sorts of weird things. Strong nuclear force is really poorly understood. But what it does is it actually says that now you have gluons that are doing the interaction between the protons and neutrons, and that interaction is very powerful and keeps the nuclei from going on top of each other. So the inner 3/4 solar mass of the core, that just stops. So everything else starts to fall on top of it, and it springs back a bit, doing what's called a bounce. And so material still keeps falling on top of it, but now that core collapse is coming back up. And that creates a shock wave. That shock wave kicks out about a huge amount of energy, 10 to the 44th joules, which is the equivalent of about 100 billion suns. That all happens in less than a quarter of a second. And in about 20 to 40 milliseconds, which is the same time it takes you to snap your fingers, all the matter that is getting swept up by the shock wave there's a bunch of stuff that's falling down on top, and the shock wave's coming up, and it stalls because now you've got material coming up and material coming down. You've got a shock wave above it, and then the interior of the core, because protons and electrons are still becoming neutrons inside of that core as part of this compression. The neutrinos are still trying to get out, and they can't. So they basically they get trapped. Finally, it becomes dense enough for neutrinos to get trapped. And by trapped, I mean 1 out of every billion or so. The other 999 million get out. But 1 in a billion, considering how many neutrinos are coming out, that's enough to do it. Those neutrinos get trapped in the gas. They then heat the gas, depositing their energy through weak nuclear reactions inside of the gas. And that turns it, because it's uneven across there, because because neutrino interactions are rare, so it's going to be an uneven sort of distribution. That leads to incredibly violent convection right above the core, which is trying to bubble away and turn itself into one big atomic nucleus. And that makes a new shock wave as the neutrinos now push the whole thing apart. About 300 milliseconds, which is just over a quarter of a second, which is also, interestingly enough, that's about as fast as your brain processes thoughts, 300 milliseconds. That's interesting to think. So as fast as your brain can process a thought, the shock wave reappears and smashes out through the star, pushing up against the infalling matter, creating massive amounts of nuclear fusion in the wake because of the high density and high temperature. That shock that comes back up, which is now a shock wave or an explosion wave, heats and accelerates the rest of the star, and the shock eventually breaks out through the surface, moving at almost 10% of the speed of light. And from a distance, we see a star that's now about the size of Jupiter's orbit explode. And that's what we call a supernova. And for a very, very brief time, within minutes, a supernova can outlast up to 1 to 10 billion times the luminosity of the sun for just a few minutes, and in fact much longer. And it can outlast an entire galaxy of stars in terms of its output of light. And the outer envelope is then blown off into space along with much of the core and accelerated to a fraction of the speed of light. So this is going 1/30th of the speed of light. That's pretty fast. And that's a really fast shock wave. It's not a pretty thing. If you were next to it, you'd be dead. It doesn't matter how close you are, you'd be dead. You can't be Superman, you'd be dead. If you were within a light year, you'd be dead. That's just how this all works out. And, well, you're not going to be there, and they're never going to do an episode of Star Trek, and I'm even sure Doctor Who would lose it on that one. Anyway, the gas will expand, eventually cooling off, leaving only the core behind. And we see in the background here a galaxy that has a supernova in it. We see the supernova on the outskirts of this galaxy. And notice how it's almost as bright as the core of the galaxy. This is a dimmer supernova, but it was seen around that galaxy. In fact, you could think it might even be brighter than the core. And remember, the core of the galaxy is composed of maybe tens of billions of stars itself. So one star is much brighter than maybe tens of billions, 50 billion stars that are deep in the core of this galaxy for just a few months. And that's what a supernova is. And this has a name, 1994D, because it was seen in 1994, and it was the fourth one observed in 1994. So that's why it's called supernova 1994D. Then this was one that I saw in 2014. This happened in the nearby galaxy M82. It was a different kind of supernova, but still the point's the same. It was a super bright star, and that bright star appears inside of the disk of the galaxy. Don't look at the star that's right above the number, the magnitude label. Look inside the disk, and you'll see that there is one star that's actually getting brighter and brighter with time, and then fading with time. And so we see that as time goes on, this particular star is getting brighter and brighter and brighter and then fading. So we definitely see the star getting brighter as time goes on. And that was in January of 2014. And I remember taking out a telescope, and when I looked at that thing, I could definitely see a line of 3 stars. I could see the 2 stars, and it's most obvious in the lower left-hand corner of this image, as well as the core of that galaxy. So this was eminently within the observational capacity of a 15-inch telescope in an urban environment. I saw it. And there's another image. This was taken by Micro-Observatory, and we see all the way over on the right. There it is right there. There's the supernova in M82. Here's another supernova in the galaxy NGC 1309, and there's a Hubble follow-up image with respect to it. The left-hand one, taken by the Lick Observatory, was in 2002. And once you run out of letters, you start doing 2 letters. So they went through the entire alphabet, and that's because F and K. What does F and K mean? Well, there's been, since 1994, serious supernova studies, so people are able to find large numbers of supernova by going and hunting for them. So dedicated supernova searches have found hundreds a year. And we see in the Hubble image from 2005, they're able to pinpoint exactly where that star was in the sky and try to look for remnants. And finally, let's look at the nature of what a supernova explosion kind of looks like. They're very, very, very luminous, and we talk about light curves, and that's why we have these images that we looked at before, is that how does the luminosity of such a star change with time? And there's two types, two general types. There are many, many, many sub-classifications, but I'm just going to keep it with these two types because it makes it a little easier to understand, because there's two principal versions of supernovae. And we're really only talking about one kind this time, which is called core collapse supernovae. And a core collapse supernovae is called a type 2 supernova, and that's the green line in the background. What you see is that there's an incredible brightening, and then it dims for a while, and then it has a plateau, a flat plateau for a while, where it stays at roughly the same brightness for a long time, maybe a month or so, and then dims again at kind of a curve, and then the curve changes shape again. Each one of those changes of curvature is a result of different material glowing. So the initial brilliance of the supernova will fade over time, and it's slow because all of the gamma rays, remember that supernova explosion had all sorts of things mixing down right above the core. And that means there was a huge amount of nuclear fusion that occurred explosively in the core, and rather rapidly. So in that explosion, it created large numbers of radioactive elements, and this primarily radioactive nickel and radioactive cobalt. We see that there is a decay of radioactive nickel to cobalt to gamma rays. Those gamma rays then illuminate the gas that surrounds the supernova and makes it glow, because the gas might be too thick to actually let the gamma rays come straight out. The nickel tends to be the thing that fades out more slowly at the top, and cobalt is primarily responsible on the right. So there are also these two types of supernovae, not just their light curves, meaning one just gets bright and then slowly dims, that's the type 1s. The type 2s have a slightly different appearance to them. Type 1s have no hydrogen line emission features, but type 2s do. And that makes sense that a type 2 supernova would have a lot of hydrogen line emission. Remember, hot hydrogen gas happens because it gets really hot, right? And so the atom gets ionized or excited and drops back down from excited states down through. So you get hydrogen emission lines in visible light. And so you should see that pinkish glow of hydrogen, or at least an emission line looking at the spectrum. That's because the outer 5 astronomical units of the star, or a significant fraction of the star, did not participate in the fusion down in the core. So it's still hydrogen. So type 2 supernovae have hydrogen emission lines, but strangely enough, type 1s don't. So core collapse supernovae are the type 2s. They do have significant hydrogen absorption lines, but type 1s don't, which is really interesting. So let's look at one in particular, one of the more recent ones that came out that happened when I just got done with high school. So when I was in high school in 1986, I graduated and went off to college and started studying astronomy, and everybody all of a sudden started talking about supernova 1987A, the first one in 1987, in February 23rd. And that happened in the Large Magellanic Cloud, and the Large Magellanic Cloud is a neighboring galaxy to the Milky Way. It orbits at about 160,000 light years away. So for a very short period of time, it was brighter than 5 billion suns, which is amazing. Finally, which made this really important, we haven't had many Milky Way-based supernovae. And now the Large Magellanic Cloud is not part of the Milky Way, and the Large Magellanic Cloud is outside the Milky Way, but we haven't seen many naked-eye supernova since Kepler saw one in 1604. So this is the picture that was taken by the Anglo-Australian Observatory of supernova 1987A. The right-hand side shows before, and since it's in the Large Magellanic Cloud, and that's a close-by galaxy, this is an extraordinarily studied area. And because it's so well studied, there's lots of pictures, and people were able to determine exactly which star it was before it exploded. And there's the star. And we can see there's the Large Magellanic Cloud itself in the sky. It's a star-forming region. It's a huge star factory. Then we take a slightly different view of it from an emission line survey on the left-hand side, and then we show where this location is in Anglo-Australian Observatory's image of it, and then we see a Hubble Space Telescope image of it being close up. So here's some of the vital statistics for 1987A, which was a supermassive star. Has a funny name, named after the guy who actually made a catalog of these large stars, these hot stars in that area. Large Magellanic Cloud, distance about 50,000 parsecs, and the type of star was a B-type star, a B-type supergiant. So it's not as hot as an O star, but it definitely is a hot blue star. And the size of the star before it exploded was about 50 times the radius of the sun. And the surface temperature was about 16,000 Kelvin. Remember, the sun is 6,000 Kelvin. So the surface temperature was just only a little bit hotter, only 3 times hotter than the surface of the sun. However, the core was a different matter. The luminosity of that star prior to its explosion was over 100,000 times the luminosity of the sun, and its mass was about 16 times the mass of the sun. Now, there was another really interesting thing that happened at this exact time that the star went off. A neutrino burst was detected. There were 19 anti-electron neutrinos detected by the various neutrino observatories across the world. The Kamiokande Observatory, which is in Japan, observed 12 of those 19. And the energies of these neutrinos were about 20 mega-electron volts. Remember, the binding energy of the core of a nucleus is about 8 or 9 for iron nuclei. So these neutrinos were given almost 3 times the energy required in order to rip apart an atomic nucleus of iron, which was fascinating. So there was a huge amount of energy being pushed into neutrinos as the star was collapsing in the core. The thing that made it really interesting and this star began the process of what's called neutrino astronomy, because they were detected 3 hours prior to the light of the star. The star was observed by an astronomer because it was up at night, and it was seen in the sky at night. And he reported it the time he saw it, and he swung a small telescope over to take a picture of it when it was observing down in Australia. But because the distance to it is 168,000 light years, and because we detected 19 antineutrinos across the Earth, that meant, because of how seldom and how rarely neutrinos interact with normal matter, there had to be 50 billion neutrinos coming from supernova 1987A, arriving at Earth, at the Earth's distance from it, 168,000 light years away, 50 billion neutrinos per square centimeter. So hold out your thumbnail, that's about a square centimeter, and at that moment, 50 billion neutrinos passed through your thumb at that point from that one supernova. That meant the total number of neutrinos that was emitted from this explosion was about 10 to the 58th. That's a big amount of neutrinos. That's a 1 with 58 zeros after it. I mean, I didn't even bother to write it out because, I mean, it'd be cute and everything, but who wants to do that on this thing? And the neutrino burst lasted about 10 seconds, which lends credence to the idea that the neutrinos get all bunched up. And there were actually 2 or 3 waves of neutrinos that occurred. The total energy released in the neutrinos is about 10 to the 48th joules, which is about 10 to the, if you add it up over 10 seconds, that's 10 to the 22nd times the luminosity of the sun. That's a lot of energy. In fact, 99%, more than 99% of all of the energy of supernova 1987A and all core collapse supernovae go out in the form of neutrinos. Neutrinos carry away almost all the energy. Sure, we can see it as a bright thing. But if we could look in if we had neutrino detecting eyes, we would be blinded because there would be too many neutrinos for us to see. And the luminosity of it was astonishing in terms of how much luminosity there was in energy compared to the sun. So the peak visible luminosity, meaning how much light it emitted, was about only a measly 4 times 10 to the 33rd joules, which is only about 10 million solar luminosities, which isn't much. So that's incredibly small compared to the neutrino luminosity. It's a tiny fraction. Remember, you subtract, that's about 10 to the 15th times less luminosity in light than there was in neutrinos. Well, the material that got ejected really hard at 10 to the 7th meters per second. That's about 3% the speed of light. And about 4 solar masses of material got ejected from this supernova. And it imparted 10 to the 44th joules of energy. So the kinetic energy of the material is comparable, or at least it begins to be comparable, to the total energy released in neutrinos. So the kinetic energy is about 1/100th of 1% of the neutrino energy. And just to give it a reference frame, it became as bright as a 3 magnitude star. So it was pretty bright. So if you were down there, you could say, hey, what's that new star in the sky? Because a 3rd magnitude sky under dark sky conditions, and if you know your night sky, you'd say, that's a new star. You would have noticed it. It is a distinctly noticeable star. It wasn't as bright as like -2, like Venus or something, but it was as bright as one of the stars in one of the belt stars in Orion. That's as bright as that. Or one of the brighter stars in bright constellations, such as those in the Big Dipper. So it became pretty bright. It was definitely naked eye star. But remember, most of the energy was not in light, wasn't even in ejected material. Almost all of it was in the neutrinos. However, that doesn't stop people from looking at stuff. And what's really neat is the American Association of Variable Star Observers had a number of people who went and took a look. And what we see is this is the light curve from visual observations of supernova 1987A. And this is in the V magnitude, and we see people making magnitude measurements over the course of time. And this can be downloaded from the AAVSO.org, and it shows that it was caught before the peak occurred, then the peak occurred, and then it had a plateauish sort of long slope, and then it had another drop-off. So the first peak, when it was observed, was the initial explosion, and then it got brighter as time went on because nickel-56, which is radioactive, decays to cobalt-56, and which is also radioactive. So the nickel has a very short half-life, and that's the first decay of the curve, and it got brighter because that stuff was seen. As the shroud of gas was revealed, it got brighter and brighter and brighter. So the first slope down is the dimming as the nickel-56 finally decays and becomes cobalt-56. Then that drops away. There's not much nickel-56 left. We got a bunch of cobalt-56, and so we got this longer, slow, slanted curve, and that shows it decaying to normal iron-56. So iron-56 is the most common thing in the universe because everything more massive than it, or at least many of the products that would be formed in supernovae, decay to iron-56. And then it kind of has a nice little curve at the bottom, and that's just the remaining gas and dust being heated by X-ray emission from residual things as well as shock heating from around. And it got dimmer and dimmer and dimmer. And once it got below magnitude 6, it was below naked eye view, and then people were using telescopic views all the time. So that's really interesting. And we see how long it takes for these things to go. And you can see that it was observed in February, and it was a big burst of observations right there, as people ran to their telescopes in order to make these strong observations. And if you went to the AAVSO website, you'd see how many people actually participated, which is a lot. So later on, we see images of rings surrounding supernova 1987A, and the bar shows the angular diameter, which is 1/60th of the angular diameter of the moon, which is about one half of an arc minute. So that shows it's not very big in the sky, but at least it's noticeable in a small telescope. So when this was looked at, it was determined by subsequent Hubble observations that this glowing ring exists. These rings, that really bright ring in the center, has been there for about 20,000 years before the star exploded. And when the X-rays from this explosion energized all the gas, it's making it glow. And all these things, these blobs, are moving really fast, moving at about 20 million miles an hour, and that creates a shock wave of material that slams into, and that shockwave material heats it up and makes the material in the surrounding medium, the surrounding interstellar medium, glow. So there's the glowing material moving at millions, at tens of millions of miles an hour, slamming into the interstellar medium and causing it to be hot and emit X-rays. And there's also these kind of interesting bubble shells as well, which are like light echoes. And we can see that the Hubble Space Telescope imagery from 1994 to 2003 shows the evolution of this ring. The initial ring was heated by X-ray emission, and then as time went on, the material from the supernova slammed into that hot ring and made it glow brighter. And there we see a detail. There we see a brighter detail showing the knots of hot gas that's been heated to tens of millions of degrees. It also emits X-rays. And how did this actually come about? What's different about this? And we're going to go into this a little bit later too, but let's look at how supernova 1987A might have arisen and where those rings came from. Probably the star was a binary system, and the more massive star evolved first, became a red giant, and as it became a giant, it literally engulfed its close companions. So these two were incredibly close stars, and then the two stars, one star got larger and larger, and that provided drag on the other star. Third, the two stars, in so spinning, most of the star, the red giant, got pushed out into a spinny envelope to conserve angular momentum as one part merged and the other part expanded away. So then you have this ring that's been expanding away as the two stars now merge together into one. Then as they merge, you have basically something that's very similar to a protoplanetary disk like we saw in the interstellar medium stuff. And that's what the bipolar outflows of gas made this ring-like structure in the bubbles above. Finally, then, there's a massive explosion that occurs, and that's the supernova that we saw, all in bright light. And then the ejecta start to move outward, and once the ejecta then from the supernova slams into the disk, it makes it glow and forms those beads. So there's the story of how people think it actually worked. And so you have all these knots of gas and dust. There's bipolar flows, meaning that's what that inner glow is about, from the jets that occurred from the supernova as the material flows outwards. So there's some hot material sitting there. And yet, this should have formed some sort of neutron star or black hole, but it isn't seen yet. And it basically has not been revealed yet because the gas density might be too high. There's no reason to think that it's not there yet. It's just hidden for some reason. Maybe it got ejected and shot out to the left or something like that and left the entire area. But there should be some kind of disruption if it did that. And angular momentum would say that it would probably be shooting off into the ring structure around it. Anyway, we see that there's a pretty interesting explanation for those fun ring structures of supernova 1987A, which was the nearest supernova to us since 1604. And why we care about supernovae, and we're getting close to the end here, so bear with me, is because nucleosynthesis is where we get all of the elements in the cosmos. We start the universe with hydrogen and helium. The Big Bang made hydrogen and helium, but stars make everything else. The iron that you use that is in your blood was formed in a star. The nickel that you pay a piece of candy for at the nickel and dime store, that was made in the center of a star. The universe started out with about 75% hydrogen and just under 25% helium and little bits of lithium, boron, and beryllium, but nothing else. Every other element were fused in nuclear reactions inside of stars, and all heavy elements above iron are formed in supernova explosions of various kinds. So the 10 most abundant elements in the entire universe are hydrogen, helium, starting at the top, all the way down to sulfur and magnesium. And notice what's interesting about what we see in the topmost 10 abundant elements is that many of them, like magnesium, carbon, oxygen, nitrogen, iron, those things are really important for life. So the elements that make up life are incredibly common elements in the cosmos, and they're also small on the periodic table. We also see silicon being a very large amount that was formed. And notice what the Earth's crust is made out of mostly, primarily silicon oxides. And so that shows where planetary objects come from. So Planets are made from silicon and iron predominantly, with all sorts of other stuff and carbon and oxygen, and life uses those common elements in huge amounts in order to metabolize and live. So what happens to that supernova remnant, such as 1987A? Well, you get all sorts of all the materials that were made in that, all that fusion-enriched stuff was made in the explosion. It expands at thousands of kilometers per second. That makes a blast wave. As we saw with 1987A, it plows into the interstellar medium. It stirs the interstellar medium. It makes an ionized nebula that can be seen for thousands of years. We'll talk about supernova remnants next time. But that makes something to be seen for a few thousand years after the explosion. And that material then mixes with the interstellar gas. That mixed gas becomes part of the next generation of stars with these metals, and then the next stars are more metal rich. And by metal, I don't mean like iron and nickel and so forth. I mean any other element heavier than helium. That's what astronomers call metals. That's a really funny thing. So metals are things that are heavier than helium, and all successive stars have more of it as a result of that. So the material that was formed in those supernovas goes out into space, and all of the things that are us that were formed in some supernova long time ago in the same galaxy. And therefore the solar system itself formed 5 billion years ago by gas that was enriched from these massive star explosions. And so stars form, they evolve, they live, and they die. And then they push out that stuff into the interstellar medium and make more stars. And that's what we mean by this thing that we saw earlier on, that this beginning stars start from clouds of gas and dust. They form protostars. They go through their main sequence lifespan. They then become red giants or explode as supernova. If they become red giants, they puff off their outer layers as planetary nebula. The more massive red stars, like a little bit more massive than the sun, churn out a lot of carbon before they do that. The most massive stars go into these core collapse supernovae and explode wildly in order to make these type 2 supernovae. Sometimes they'll form a neutron star, and sometimes they'll form a black hole. The most massive stars at the top of this thing can go straight to a black hole, and that's really interesting. And we'll talk about those when we talk about gamma ray bursts. But for now, notice the cloud on the left forms stars that are protostars, and stars become that way and they shed their outer layers or explode or something like that, and seed the right-hand side of this, which is more and more and more gas and dust. And that then loops around to the left with those small mass stars at the bottom and the high mass stars on the top, with 80% of all the stars in the Milky Way just brown dwarfs and red dwarfs, with the rarest of things, the tiniest sliver of stars become blue giants, blue supergiants, and explode violently in these ways to make supernovae. All right, so that's more about supernovae, and we'll be talking about their remnants next time. See you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be finishing off our exploding, dying stars and the lives and deaths of stars with supernova remnants, some of the most beautiful objects in the sky to go look for with a telescope, and to look for with telescopes that aren't your eyes, meaning something up in orbit, or a Hubble Space Telescope, or an X-rays, or infrared, or gamma rays, or so forth. Because supernova remnants emit huge amounts of light, that is a very, very strange source of light, and unlike stars. So these are the bits from the dead stars that we saw last time when we looked at supernovae. All right, so let's review again what supernovae are. Supernovae come from extraordinarily large stars, stars more massive than, say, 5 to 8, roughly 10 times the mass of the sun, which are the top 3 rows, or more specifically, the second and third row from the top, and we see that there's two types of stars: blue supergiants that become type 2 supernovae and become black holes, or it becomes a supergiant, a blue supergiant that becomes a type 2 supernova and forms a neutron star. So these are the kinds of things that we're going to be looking at today. Okay, so remember again, stars that are really massive, above 10 times the mass of our sun, will end their lives catastrophically in a massive explosion that can be seen for many, many millions, if not billions of light years away, as they outshine their entire galaxy when they explode. And when they explode, they create all of the abundant elements in the universe. Anything bigger, more massive, meaning any element on the periodic table greater than iron, which is Fe on this thing. Fe is 26. Look at the fourth row right in the middle. Iron is Fe. And that's the heaviest, most bound element in the entire periodic table. But everything larger, below iron and to the right of iron and down from iron and higher atomic number than iron, was made in some sort of supernova. So these top 10 elements, in terms of their most abundant, it's hydrogen, helium, oxygen, carbon, all the way down. Notice they're all less massive than iron. But all the important things for life, like carbon and oxygen and nitrogen and iron itself, well, hydrogen do because of water and acids and bases and all sorts of things that hydrogen provides, that's where they come from. So nucleosynthesis occurs in the largest stars. They all fuse hydrogen into helium as part of their main sequence lifetime. But when stars are much, much older or much, much bigger than the sun, about 8 times the mass of the sun, they will convert light elements all the way up to iron and nickel, and then those accumulated layers, and then there's an explosive fusion that happens that builds even more light elements up to iron and nickel, but that also sets up a huge number of reactions that inside of the explosion, where the densities are extraordinarily high inside the core of the star as it's exploding, that create huge numbers of very heavy elements all the way up to, say, californium, which is 254 atomic nucleons in its protons and neutrons inside of its nucleus. So these things get all created, the vast majority of which are radioactive and then decay back down all the way down to iron. So the more massive things decay back down to iron or find a stable nucleus that doesn't decay. And then we find that supernova explosions are literally responsible for creating every one of the heavy elements seen in nature, except for hydrogen and helium, which were formed in the Big Bang. So supernova remnants, these things are the exploded elements of the star, because most of the star gets blown apart when it explodes, when these massive stars explode. So of a 10 solar mass type star or a 20 solar mass type star, perhaps 10, if it's a 20 solar mass star, perhaps at least 10 solar masses gets exploded out into the cosmos as a result of the explosion, where some of it may fall back down to a neutron star or a black hole, but some of it was ejected as part of the latter portions of the star's life and forms a nebula around it. And if there is a nebula around it, then the supernova's light can slam into that nebula and illuminate it, like we saw with supernova 1987A. And the blast wave then can plow into the interstellar gas, which is partly created by the supernova itself. And then it stirs and heats up the medium, and it makes it hot enough. And this kind of nebula lasts a couple thousand years for after the explosion. So this leads us to the concept of stardust. The metal enriched, and by metals we mean any element heavier than helium. That's what astronomers call metals. Metal enriched supernova, it mixes with the interstellar gas that creates new stars, that becomes part of the new star mix, because stars are almost all hydrogen and helium. Remember, the oldest stars have very little of elements heavier than hydrogen and helium, but the very youngest stars, meaning stars formed within the last 5 to 10 billion years, do not have or have a significant enrichment of, say, carbon, nitrogen, oxygen, iron in their atmospheres because of the previous stars out of dust out of which they formed. And that's where the silicon and oxygen and carbon and everything that we know of that makes up the entire planet Earth was formed. It was formed inside of a star that exploded maybe 5 to 10 billion years ago. And the material then floated around the galaxy, floated on the Milky Way until it combined with another interstellar cloud. That interstellar cloud collapsed, as we saw, just like the interstellar medium and star formation in previous lectures, that it collapses down and forms other stars. So the solar system was formed from a gas enriched by previous generations of massive stars. And that's where all the planets come from. And therefore, star formation is cyclical. They form, they evolve, they die. And they make more heavy elements that then go out into the interstellar medium. And what this does is it actually takes away some of the hydrogen in the galaxy. And so much of the hydrogen can be used up. If there's not a lot of hydrogen gas, then you can't have star formation. You need to have a big cloud of hydrogen gas. And eventually, that will all be used up, and they'll be just stars or just dust. And if you just have dust and just have stars, you can't form new stars. And we'll see in the galaxy section that there are certain types of galaxies, like ellipticals, that don't have any star formation going on. So they have very, very, very low metal type stars. Anyway, that's where stars come from. That's where so today what we're going to talk about are some historical supernovae that actually light up the skies today. In 1054, there was a guest star in the constellation of Taurus. It was seen by Chinese astronomers way, way back in 1054, and it was visible during the day for about a month and visible at night for almost 2 years. I think I got the wrong number here, 6 months. No, actually, it's closer to 2 years. And this thing left behind the Crab Nebula, or Messier object number 1. And in 1572 and 1604, 2 supernovae occurred. The one in 1572 was written up extensively by Tycho Brahe. In 1604, Johannes Kepler wrote extensively about the supernova he observed. Now, they weren't the only people who did the observations. It's just they're the people who wrote the most about it, so we basically named the supernova after them. But there were numerous people who were watching the skies at that time, and they all saw this happen. So it wasn't just like some guy saw it. No. Everyone on Earth saw it because they were bright enough. They were incredibly important supernovae, and they influenced astronomy and modern culture of their era. This is pretty important to remember how devastating these things could actually be for culture on Earth. And finally, we'll also talk about a supernova that happened between, say, 6,000 and 8,000 BC, the Vela supernova, and it was observed by the ancient Sumerians, and it appears in some of their ancient legends. So first, let's look at the Crab Nebula. The Crab Nebula is very, very prominent in the sky, and the Crab Nebula itself is something as by Messier object number 1, the first in Charles Messier's catalog of the 1700s. He actually went outside and looked at it and found this fuzzy patch in the sky and said, oh, that's not a comet, so I'll make it my list of things don't bother looking at because it's not a comet. However, back in July 4th of 1054, Chinese astronomers saw this new star in the sky, and it was much brighter than Venus, and it was visible during the day for about 2 years, and even it was seen by numerous cultures across the world. Well, that exploded back then, and here's some vital stats about Messier object number 1, the Crab Nebula. The mass of the progenitor star was about 9 times the mass of the Sun. The amount of ejecta inside the nebula that you see in the inset was about 2.5 times the mass of the Sun, which is an enormous amount of material. And there's a central neutron star, which we'll get to in the next set of lectures, and the central neutron star is about 1.4 times the mass of the Sun. The distance to the Crab Nebula is over 6,000 light years, so to have something so bright that it outshines Venus and can be visible during the day, 6,000 light years away, almost 6,500 light years away, meant it was extraordinarily bright in the sky. And if you go taking a peek at it, the angular size is about 5 arc minutes by about 7 arc minutes. And remember, there are 60 arc minutes in a degree, so it's actually a rather sizable nebula in a small telescope. I have hunted for it repeatedly, and I've always found it to be a very unsatisfying nebula. So you should if you want to go see it, you got to go see it, try to get it photographically, or what you want to try to do is use a very large aperture scope of at least 15 inches or greater in order to see it. The radius of it depends on which angle you're looking at. It's about 4 light years across one way and 6 light years across the long way. And the speed with which the material that you see in INSAT is going is up to 1,500 kilometers per second. So that's really cooking by. The total luminosity is much, much, much greater than the sun's at about 1.38 times 10 to the 34 watts. And the total amount of energy that's coming out in X-rays is just under 10% of that. Now, most of the luminosity, a significant fraction of luminosity, comes out in radio light, and that's in fact, this is a significant fraction of the total luminosity is in radio frequencies. This the field. What you're also looking at, the nebula itself, is permeated by a very strong magnetic field that is much, much stronger than the Earth's magnetic field, and the formation in order to create the nebula itself, or create the formation of this thing. What energy did it take in order to make the neutron star that's powering the appearance of the nebula? It cost an enormous amount of energy, much more energy than the sun will put out in its entire lifetime. In fact, that's more energy than 1 billion stars will put out in 1 second. So there's this pulsar that's emitting radio pulses in the center that goes every 300ths of a second. So that's faster than you can snap your fingers. Something is blipping out there, and that blipping is slowing down by about 100,000th of a second per year. And that's called a pulsar. And we'll talk about pulsars and neutron stars next time, but I just wanted to show you that. So the Crab Nebula has many observational characteristics, and so we see the Hubble Space Telescope image taken with the Wide Field Planetary Camera 2, and this was taken by Hester at Arizona State University with the Hubble Space Telescope. And we see that the Hubble can see it's a narrow band filter set, and we can see that it looks like an astonishing wreck. And the changes are actually easily seen by going back and looking at the Crab Nebula over time. Now, why it's called the Crab Nebula, it's kind of weird. It doesn't look much like a crab to me. But when the Earl of Rosse looked at this with his Leviathan telescope, which we'll talk about when we talk about the Great Debate of the 1900s, about the distance of the spiral nebulae, Earl of Rosse looked at it, he sketched it, and he sketched a crab. I guess that's what he saw in a telescope visually. So, before photography, people made sketches, and that's his sketch was of a crab. So that's what he called it, and the name stuck because the crab. Why not? So we see other images on either side. The upper left is X-ray emission at various frequencies. On the right is high-energy X-ray emission from the central region, and we see some bright dot with some disk-like structure and some sort of jet. We also see the superimposition of the X-ray image on the upper right, superimposed on the Hubble Space Telescope and in Spitzer Space Telescope image in the lower right. And we can see that the X-ray luminosity comes from a sizable portion of the image in the center. And then if you take an image and put a polarimeter inside it and look at sub-millimeter wavelength, which is much, 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 much longer than infrared, and that's what you get in the lower left. And you get a polarized image of it. And the polarimetry gives you the fact that there's a strong magnetic field. So let's look first at the polarized image. This was taken with a large apex bolometer camera at 870 microns. Remember that the typical wavelength of light is this is just under a millimeter in wavelength, but wavelengths of light are 10 to the minus 7th wavelengths, or 1,000 angstroms, or approximately 10 to the minus 7th meters, or 1/10 of a micron. So this is about 1,000 times the wavelength of visible light, and that's the blue, red, and yellow that you see in this. But the lines indicate the polarization of the light. And so how you get the polarization is you put a polarizing filter, which we talked about in one of the earlier lectures, and a polarizing filter is basically a bunch of slats. And these slats go in front that only allow light whose electric field is vibrating in a particular direction to come through. And then you look at exactly where it is brightest, and that shows you the orientation of the polarization. And the Crab Nebula is strongly polarized, which indicates that it has a strong magnetic field, which is shaping the emitting electrons' orientations. So something is making it polarized. And this was given at a proceedings of the SPIE in September 12, 2012 with the introduction of this camera. Well, the explanation for all of the light that's coming from the Crab Nebula comes from synchrotron emission. So what is synchrotron emission? Well, if you take a very strong magnetic field and you accelerate electrons somehow up to nearly the speed of light, they will spiral around the magnetic field lines and travel along these helical paths at nearly the speed of light and spin and spin and spin. And as they go around in these helical paths, because they're accelerating, moving in a circle, but then that circle is getting dragged along upwards, as they're circling in the magnetic fields, that's an acceleration because a circular motion implies an acceleration towards the center of the circular motion. That means they will emit light, and they emit light in a specific way, and that specific way is given in the graph on the lower right. So a single electron is given in the upper right of the lower right of that thing, and it shows what the emission is like for a single electron. Now, if you have billions upon billions, or 10 to the 37th electrons, or 10 to the 50th electrons, something like that, spiraling around magnetic fields, you add up all those individual contributions, and the slopes on the things that go down to the right show you what the sum of all the contributions are, and it makes like a flat power law. It makes a yellow dashed line where you can say, oh, this is the power law emission of synchrotron radiation, which means that the nebula is not hot. It's not hot in the sense that we think of hot, because this is non-thermal emission. And non-thermal emission means it doesn't all have the same temperature. Now, if you had this gas that's going, really, really fast at nearly the speed of light, and it's mostly composed of electrons, you'd get hurt and it would give a sting, a burn. But when we think of things that are hot, we think of things that all are at the same temperature, and all have this, and that temperature characterizes the average motions of the randomness of the gas or solid that you think of. So on a hot day and a summer night, the air is hot because it has been warmed by the sun, so all the molecules in the atmosphere get warmed, and so as they get warm, they all move fast on average. But when you look at synchrotron emission, there's nothing for the electrons to bump into. So unlike the gas in the atmosphere when it gets on a hot day, the atoms and molecules in the Earth's atmosphere bump into each other and transfer energy until they all are moving roughly at the same average speed. Some are moving faster, some are moving slower, but the temperature can be roughly the same. That's why we call how hot is it out. But the electrons in this magnetic field don't bump into each other. They simply spiral around the magnetic fields and emit light. And this emission of light is called synchrotron emission, radiation. And it's not thermal. It's not a thermal process because they're not bumping into each other. Now they're moving fast, but they're not bumping into each other and interacting to average out the speeds. And the electrons themselves are moving so incredibly fast. They're moving much faster than can be done in any particle collider on Earth by hundreds of times. So something's driving the energy of the electrons inside the Crab Nebula up to energies that are much greater than we can do in the Large Hadron Collider. And so here's another view of what we mean by that, of the electrons spiraling in a magnetic field, and as they do so, they emit light. And on the left-hand side, what we do is we see two types of emission, and see that bulby sort of thing that looks like an onion. Now, if the electron is moving slowly inside the magnetic field, it's accelerating towards the center in a circular orbit as it orbits inside a magnetic field. And if it's moving slowly, then the electron emits in all directions, and the light is not polarized. But if it's moving very, very, very fast, nearly the speed of light, then it actually gets narrowed and polarized into a beam, because that bulb now that's shooting out to the side, that's the shape of the emission of the electron as it spirals around. It doesn't take the emitting in all directions. In the electron's frame of reference, it is. But to an observer away from the electron, it does not. It looks like it's going in these beams. And that is an effect of general relativity, or special relativity more specifically. So as you spin an electron faster and faster and faster, it gets the light that it emits from synchrotron emission gets beamed and polarized. And it gets polarized along the edge of the circle that is being polarized along. So we can see that this is a bulb sort of shape, and it's also a flat, tall bulb. And the flat, tall bulb is the orientation of the polarization. So the Crab Nebula emits enormous amounts of X-rays, and these X-rays are also emitted through the synchrotron process, and we can see pretty easily inside this thing that there's these strange filaments and like bay-like structures and loops and curls, and what we're seeing here is something that's approximately a couple light years across, and right in the center is the thing that seems to be driving it. There is some sort of disk of material that seems to be spreading outwards from it, and there's like a jet sort of puffy thing coming out from the center, and that thing that's in the center is called a neutron star, or a pulsar, because it does pulse in a certain way, not in and out, but rotationally it pulses. There's a pulse associated with its rotation, but it's rotating very, very, very fast, about 33 times a second, and it's a very tiny object, and we're going to discuss what those kind of things are later. But the energy of this object and the density of this object and the provides all of the electromagnetic energy to fuel the electrons to spiral in the magnetic field such that they can spiral around in that noodly looking magnetic field structure and emit X-rays via synchrotron radiation. And if we look closely at this, we've now overlaid the X-ray image in purple on top of the Spitzer image, which is in red, and the yellow, which is the Hubble image. And remember, it's about 4 light years wide and about 6 light years long. So the X-ray image is emitted from an area that's about 2 light years across on either side. So that jet, that plumy jet in X-rays, is about a light year long. That's coming from the center, which is that bright dot in the center, and that is the pulsar neutron star that is causing all of this damage. And there's a close-up of it, and we can see that there's a bright dot. Don't worry about the bluish bright dot right above the central bright dot. That's a foreground star. But what we see is that there is there's a disk-like structure, and this has been shown to be moving and rotating, and we'll talk about more about that when we talk about neutron stars next time. So synchrotron radiation, though, is and the reason we think that this is the case is that the emission that's happening is so incredibly vast from these things that the X-ray emission would be so great that it would actually lose its energy because it's spiraling out, it's emitting energy, so it doesn't do this forever. So it loses its speed as it's moving and therefore spirals down, and so the electron then, instead of emitting X-rays after a few, like about 5 or so years, it then slows down until it's emitting light only in radio frequencies. And when it's emitting in radio frequencies, it'll take about 1,000 years for it to slow down where it's not doing that either. So synchrotron radiation spans from X-ray to optical light to radio light. And that's why the Crab Nebula has incredible amounts of radio emission, because there's still a ton of electrons spinning around that are being replenished by this pulsar that's at the center. Now, another bright supernova is the one that was observed in 1572. There were a couple of really important cultural things that happened around this time, and in between November 2 and 6 in 1572, there was a bright, bright, bright star in the northern sky in the constellation of Cassiopeia, and in fact, you can see it in this image. I'm going to use my mouse to pass over the Cassiopeia. We see the W of Cassiopeia, and we see the bright star below it. Now, Tycho Brahe made his name on this. He was really good at actually being a publicity hound, and he wrote extensively about this in his book De Nova de Nullis Aviae Memoria Prius Visa Stella, meaning the new star. And he published it 3 times, once in 1573, again in 1602, and finally a 3rd time in 1610. And it contains all his observations and the analysis of some other observers, including some of his competitors who he disrespected and threw some shade on, which was really kind of cool. But when it first emitted its light, it was brighter than Venus, and in fact, it was even used as the opening line in Act 1, Scene 1 of the play Hamlet. And so if you go take a look at it, remember the play Hamlet is actually called a disaster. Not just the tragedy of Hamlet, but is the disaster of Hamlet, meaning bad star. So disaster, meaning bad star, was actually part of the vernacular and part of the thinking of both mythological and superstitious thinking said that if you were born under a bad star, and you can even think of Romeo and Juliet as being star-crossed lovers. So with these disasters, and if you have a disaster, you would write about it, and that's what Shakespeare did. Funny enough, there's also references to Tycho Brahe's subsequent difficulties with the King of Denmark, because that's where he lived. And on the island of Uraniborg had some other names as well, such as it was pretty close to the island of Elsinore. And in fact, Tycho Brahe had two kinsmen. One of them was named Rosencrantz, and the other was named Guildenstern. So those two characters appear prominently in Hamlet as well. So there's a very strong link between this supernova, Tycho Brahe, and the play Hamlet by William Shakespeare. And this is the observation that Tycho Brahe did in 1572, and we can see the star marked by the letter I as being the new star, or Nova Stella in Latin. And we see the W of Cassiopeia that he drew out in the stars G, C, D, E, and F that make out the W of Cassiopeia. And it was bright enough to be seen for a very, very long time. And we call this supernova 1572A because it's the first supernova of 1572 that's recorded. And on the lower right, what we're seeing is an X-ray image taken by the Chandra X-ray Observatory after it was launched by the Hubble Space Space Shuttle. And if we then go look in the infrared with the WISE observatory, which is the Wide Infrared Survey Explorer, Wide Field Infrared Survey Explorer by NASA Jet Propulsion Laboratory, Tycho supernova shows up really bright in infrared as a spherical distribution. And that's because as the material from the supernova plows into the interstellar medium, it warms the gas and dust around it. And there's a bunch of gas and dust that you can see from the nebulosity that surrounds it. And it's heating that gas as the supernova material plows into it and warms it up enough to see. So Tycho's supernova also has some very interesting appearances. It's got this mottled sort of appearance, and it's brightly emitting in X-rays. And there's actually some different wavelengths of X-rays that are shown in these colors because of the different colors. The starry background is, of course, not X-rays. That is a digital sky survey that was just put as a background image just to show you what it looks like in the sky, if we could see it. But the foreground is the supernova remnant itself from 1572, and it was actually visible until about 1574. So it stayed visible in the sky for just about almost 2 years. Then in 1604, Johannes Kepler saw a star in the sky that was even brighter. And he wrote a bunch of things, and his book was called De Stella Nova Independere Serpentiarii, which is the star in the serpent bearers, which is Ophiuchus, Ophiuchus, the serpent bearer constellation. And those two stars that erupted forth in 1572 and 1604 assisted Galileo and Kepler and Brahe and many others in saying that Aristotle's ideas of the cosmos, that the heavens are unchanging and immutable, was wrong. And that was a philosophical change, because if the stars could change, then perhaps the Earth could move around the sun. And that was the big, big, big argument of the day. Does the Earth move around the sun? Copernicus said as much, but only published after his death. Galileo went into house arrest because he asserted that, and Kepler was just simply wandering around Europe trying to do the mathematics of it and trying to understand how it actually worked. Went over to Tycho Brahe, who Tycho Brahe himself didn't think that the Earth went around the sun, but he kind of made something modified. But Kepler eventually took the idea of the unchanging heavens being gone and replaced it with the Earth going around the sun, which then subsequently came back to Newton. Well, subsequent to that, the Hubble Space Telescope did a good observation of Kepler's supernova 1604A, and this is the view with the advanced camera for surveys that was done in August 2003. And we see the Hubble took a bunch of images in various narrow band filters that allowed it to look at specifically the light emitted by hydrogen, nitrogen, and oxygen, these specific things. And that's what you'd look for in a nebula such as this, because it won't be a thermal nebula, so you don't use a wide band filter. Use a very, very narrow band filter and look for bright bright emission. And hydrogen should be expected from a type 2 type supernova, which has exploded outer rim of a star, and nitrogen and oxygen should also be there, and that's what's seen. So the whiteness comes as a mix of hydrogen, nitrogen, and oxygen as it plows into the interstellar medium. The red is, of course, the hydrogen that we know from old, and then the rest is starlight in the background. And so the puffy, cloudy nature is the supernova remnant from that time. However, that's not the only view. The Chandra X-ray Observatory and the Spitzer Infrared Observatory also take a look at it, and it looks completely different in those views. In the blue is the Chandra X-ray high energy X-rays, and those things come because as the material from the supernova, which is traveling at thousands of kilometers per second, slams into the interstellar medium, it heats the interstellar medium and makes it glow in X-rays. And that's what that blue glow is on the outside. As the material shock heats the interstellar medium into glowing to X-rays. So basically, you've got some cloud of gas and of hydrogen gas sitting around going herp derp, herp derp. Not what I'm going to do. I'm some molecules, and all of a sudden something comes along and hits you going 10,000 kilometers per second. You're going to be angry and emit some X-rays too. So behind that shock front is a cooler X-ray emitting gas. That is the thicker interior shell. That is the heated material that's behind the shock front that is occurring from the supernova. And finally, we see in the upper right of this image the optical image of Hubble Space Telescope, which actually traces the upper right area of the supernova remnant, as well as the Spitzer infrared image, which mirrors kind of the low energy X-rays. And that comes from the fact that we have the cooler interior material that is the slamming into as the interstellar medium itself. Some of the dust doesn't get as it cools, as it is also warmed by the X-rays, and as it's warmed by the X-rays, it glows in infrared. So that's some of the remnant dust that survived, that then glows that glows because of the brightness of the X-ray emitting material that's coming through it. So let's take a look close up of the three regions. There's one region in the upper right of the remnant. And we can see in X-rays it's glowing brightly, and in the visible light it's glowing brightly, and in the Spitzer Infrared Telescope area it's also glowing brightly. And that's because as the shock front interacts with the interstellar medium, and that's must be a place where there's a particularly large interstellar cloud. Now, we talked about the interstellar medium as having cloudy structures, and they might be dark clouds out there, and this is just the supernova remnant slamming into one of those dark clouds and heating it up until it glows in X-rays, and then those X-rays then illuminate some of the dust, and that dust glows in infrared. And those X-rays also then cool off some of the things and make the gas, the hydrogen gas that's inside of the gas cloud, glow. So it illuminates this little poor hydrogen cloud of gas and dust that's now getting whacked and heated to X-ray emitting temperatures. Now, what's funny is you can actually use this to actually determine the distance and the speeds. So what a number of researchers have done is actually taken the Hubble Space Telescope, actually taken repeated images of the Hubble over periods of time, and looked to see what's moved. And when you see what's moved, then you can determine how fast it's been moving, and that's how they determine the velocity speed, by taking subsequent images and differencing them, and you can see how fast it's moving. So the bright shocks are not moving as fast as the really, really, really faint shocks. So the faint shocks are the ones that are plowing out straight out from the star, but the brighter radiative shocks happen as those faint, really high-speed shocks keep moving along as they have gone through the cloud, and then the others just glow because, well, they've been kicked. But in the same sense that, imagine you have something going really, really fast, and it's a small, say, car, and you hit a big car with a small car. The big car is going to move a bit, but the small car is going to keep on moving if it's small enough, and the big car might just keep on going. But it's more like maybe you have 1,000 little cars and one big car, and sure, a few of them are going to hit the big car, and as a line of them go by, but the debris will heat up and make an explosion, and the other ones will keep going on by. So it'd be kind of like a grand chase across the desert with a line of cars. I don't even know what I'm talking about with that. But anyway, there's a shock wave that occurs because the gas from the explosion, the initial explosion, moving about 2,000 kilometers per second, that then slams and heats into and starts into motion the interstellar medium at about 100 kilometers per second. And it's found by just looking at the difference in brightness between the three filters of hydrogen, sulfur, and oxygen, that there is a significant overabundance of nitrogen in this supernova, which leads to understanding that it's a type 2 supernova. And then we can look at, that's how it's also, the distance can be found. And here's how the distance is found. We take two consecutive images spaced almost 20 years apart, and you can see that the actual shock wave has changed with time. So the green is from 2003 and the red is from 1987, and actually a ground-based image. And then that 1987 image was compared against the Hubble 2003 image, and it showed a proper motion of about 1.5 arc seconds in about 16 years. When you know, and that is assuming a radial velocity perpendicular to assuming a radial velocity across the sky, that gives you that makes it like a base of a triangle, and that gives you the speed, first of all, of 1,600 kilometers per second at a distance of over 12,000 light years. So you can actually determine the distance by the proper motion of these objects as they cruise across the sky. And it's Sankritanal that gave this particular one, that image right that we see here. Next we have the Cygnus Loop, which is an amazing, amazing thing to go check out in a telescope. Many of the features that you see here, and yes, the loop itself is much, much larger than the full moon, so you can't actually see it, the whole thing, in an individual telescope. The Cygnus Loop, which is an enormous shock front, is moving at about 300 kilometers per second, over 1 million miles an hour. It's over 5,000 years old. It's over about 100 light years across. And if we think what was happening about 5,000 years ago, that was when the first civilizations were appearing. And so this is in Cygnus, which is a northern hemisphere bright star. So over 5,000 years ago, the first empires were built, the first cities were being built, the first Greek civilizations were being built, and there was an eruption of civilization at the time as this new star was gracing the skies above these people. And there's some beautiful pieces of elements of this thing, which is one of the wisps inside it called Pickering's or Fleming's wisp. And then there's the Western Veil, which sometimes is called the witch's broom, because the witch, which is that star, is riding the broom. And if we then look deeply with the Hubble Space Telescope into one of the elements of the witch's broom, we can definitely see that this looks like a shocked, heated region with these wispy, wispy things moving quickly across the sky. And as they move, this is visible light now, not X-ray light. But the visible light image, as the shock wave interacts with the interstellar medium, it heats it to X-ray degrees, and then that cools off and glows in visible light. And you can definitely see that this is mixing with the interstellar medium, and this is the process by which the materials in the star go out into the interstellar medium, merge with it, become part of it, and then initiate and then help to form more things, or actually seed new stars with the materials that could become planets. In this image alone, there's probably more hydrogen, more carbon and oxygen than there is in all the Earth, which is an astonishing thought to think, that that's how much material is in just these wispy looking clouds. Next, we can say how far the Cygnus Loop is, because with the Hubble Space Telescope image from the Wide Field Planetary Camera 2 that we see in the back, this can be viewed over a couple of different observations by looking in that upper area where it's very, very thin, where you can actually see the shock wave move over time, and then looking at how fast the width of the line, the width of the emission line in the upper left, shows you how fast it's moving. So the spectrum width shows the speed that the shock is moving. And so now you know that it's moving 170 kilometers per second. And then what you do is you go back and see what the angular motion is across the sky over years, and that tells you how long it took to get from where it is to go to the center. And that shows you how big this thing is and how old it is. And again, that allows you to find the distance to it. Now, you can see in these two images that there's the wide field planetary camera image of distance of only a difference of only 4 years is able to actually discern a change in position of these wisps. And with that proper motion change of the wisps across the sky and the speed derived from the width of the bright line inside of that, we then see that the distance is about 1,800 light years. That would have been really close to have a supernova 1,800 light years away. It would have been extraordinarily bright in the sky 5,000 years ago. It would not have been missed at all by anyone. Why are there so many religiously based civilizations that appeared 5,000 years ago? Did somebody look up in the sky and say, "This was the most important thing. I know why this star is doing this. Follow me"? Is that possible? Maybe the stars in the sky help us to change human culture. If we then look at Cas-A, which was possibly came about in the middle of the 1600s, it was a 30 solar mass star that exploded, and it has X-ray emission as well, and it is powered by a neutron star. And we find from Hubble imagery that it is extremely bright, oxygen emission, so it has an extraordinarily oxygen-rich supernova remnant, as well as another supernova remnant, N94, which is, again, part of the Large Magellanic Cloud, and so it's very tough to see from the ground. In fact, you can't. So this is a really tricky one from Hubble Space Telescope data, and that's a very distant object in the Large Magellanic Cloud, about 1,600 light years away. Here's another supernova remnant that spans about 70 light years across, and it's only about 5,000 light years away, and it's between two very bright stars, Eta and Mu Geminorum, which are bright stars in the constellation of Gemini, and it's a rather big object. The size scale that we're looking at is that this thing is about 50 arc minutes across, which means that it's actually that bubble, that red bubbly shape, is actually twice the size of the moon in the sky. But it's hard to see in the sky without photographic telescopes. In fact, it is not possible to see without photography. And the reason it's bright in the upper left-hand area of the bubble is because it's slamming into that emission region in the upper left, behind the words in this image. And so as it slams into that hydrogen gas, it makes it glow, and it emits X-rays, and that then emits visible light in the form of hydrogen gas emission. There's another one, supernova remnant 132d, and possibly a supernova that will occur in our lifetimes, which is Eta Carina, which is in the southern hemisphere. But if it goes off, we'll definitely be able to notice that, but only people in the southern hemisphere, not northern hemisphere. And the Hubble Space Telescope has been looking at it. We see observational emissions of the thing shredding itself with ionized iron and nickel, argon and helium all throughout its spectrum. Now, all of these massive stars, these supernova massive stars, can be iron-rich supernova, and that's how we know that the oxygen is actually permeating the cosmos. By knowing their distances and their expansion rates, we can compare their relative sizes. Cas-A is only about 350 years old. There's another one that's 2,000 years old, and N132d is about 3,000 years old. And all of these things are just expanding and expanding, and as they do so, they enrich the interstellar medium. And if you go out and look at other galaxies, such as M83, M83 is just creating supernovae like crazy. It's about 15 million light years away, and the smallest feature on the inset is about 72 light years. This is a barred spiral galaxy, has a starburst nucleus, and there's been 6 supernovae since 1923 that have been observed in it by astronomers. And there's huge numbers of core collapse stars in it, and at least 200 supernovas in less than 3,000 years have happened in this galaxy, only 15 million light years away. So if we zoom in on a particular thing, how do you look at this thing and determine what the supernova remnants are? Well, you look at their spectra. And the spectrum of an M83 supernova, we have 4 different lines that are actually highlighted by these different red items. And hydrogen emission is roughly the same between that and, say, an H2 region on the bottom. But a supernova remnant has oxygen emission. And so strong oxygen emission with strong hydrogen emission And even strong sulfur emission, which is the blue line, S2, and O3 is the oxygen emission in green, that tells us that it's a supernova remnant as opposed to an emission nebula such as the Orion Nebula or something. So then you go and look for these circular sort of regions that are emitting a lot of oxygen, and this is what you find. You just go in front of these bulbs, and boom, 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 people are going and hunting and going and finding them and looking and looking and looking. And in fact, this group found 60 supernova remnants inside just that image that we were looking at before. So if you actually reduce that down, that image, and play with it, you can actually find these objects all throughout this other galaxy, and they're everywhere inside there. These supernovae have been popping off all over the place. And if we then just look at the core region alone, you can see there's like 24 of them right in the core of the starburst core of that galaxy. But now I'm going to finish on one of the more interesting supernova remnants that possibly helped start civilization, or at least what we would call agriculture. And I'm going to make this assertion, and I know I'm wrong, but I'm just going to go with it. The Vela supernova remnant, about 11,000 years ago, in the southern constellation of Vela, there was a star that exploded. And when it did so 11,000 years ago, the outer layers of that star crashed into interstellar medium, making the shockwave, and that's what that fluffy shockwavy sort of puffy thing is in the center of this whole thing, by Sky Factory, which was processed by David Martin. And so this image is also visible in X-rays, and this whole puffy, cloudy sort of, that's the wispy sort of webby thing that's in the middle. That's the nebula, that's the supernova remnant. The rest of it is H2 regions and star-forming regions, but the webbiness is from the exploding star that happened about 11,000 years ago. And there's a view of it in H-alpha taken by the Anglo-Australian Observatory. So supernovae do a lot of things. If one were to go, and the last one that was seen naked eye was 1604 until 1987. That was the first one since 1604. So another one might go off at any time in our sky. There's no way to predict them. And when they do, it might cause a big change. It might cause somebody to build a new religion. But at the very least, that star's explosion goes out into the cosmos, seeds the cosmos with more gas and more dust, enriched with iron, nitrogen, oxygen, and carbon, and all the elements of the periodic table, and those then merge to form other stars, which then make new planets. So we are looking at a wisp of gas, but that wisp of gas has more mass of carbon and oxygen in it than thousands upon thousands of Jupiters and Earths inside of that wispy-looking cloud. And that's what we really think about supernovae, that they are the beginnings of possibly even the solar system. The shockwave could have begun the solar system's collapse out of this cloud of gas and dust. And we know that these elements must have been created there, because that's the only place where they would be. All right, so next time we'll be talking about neutron stars, white dwarfs, and black holes. See you soon.